Welcome to the Virtual Flow Forum for this year, all really about wastewater flow and flow to full treatment. It's such an important issue right now, as the water companies, to my estimation, are investing around about £1.5 billion on flow to full treatment, and those are involved. There's a lot of work going on. So as we had a bit of a interruption there, I'm going to go straight to Pete Baker from the Environment Agency, who's going to be our first speaker, talking about improving the regulation of flow management at wastewater treatment works. So Pete, do you want to take it away?
I'm Pete Baker. I work for the Environment Agency. I'm a senior advisor in water quality. I work in the head office, and I'm my focus is on permitting and compliance. And for the last several years, I've been focusing on flow regulation. And this presentation is about the importance of flow regulation and how it's been improved, or how we do regulation of flow is being improved. So can I have the next slide, please? So flow compliance at sewage works. Why is it important? There can be unexplained failures of Water Framework Directive standards downstream of sewage works, and the principal sort of control of sewage works that we've had for 20 odd years is, and more, but a real focus has been on discharge quality and discharge quality compliance of treated sewage effluent. And the compliance with discharge quality limits is good. It's at around or above 98% of sewage works are compliant with are not failing numeric discharge quality limits. But we know that flow is also important. So flow together with discharge quality, controls the load of pollutants, load of what's discharged from a sewage works into the receiving water. So we have dry weather flow limits in permits, which along with discharge quality control the load and the impact of discharges. We also have flow to full treatment settings within permits, and those settings control the volume of sewage that must go forward, or the rate of flow of sewage that goes forward for full treatment, with surplus excess going over into storm tanks. So having these limits, having flow to full treatment compliance limits, it's there to avoid damaging discharges on dry days, and also to allow storm tanks, once they're filled, to be emptied as soon as reasonably practicable, ready for the next subsequent rainfall event, storm. So, yeah, thank you. So, just as a mark of how long we've been looking at flow to some extent, we have a flow task and finish group, which was set up in 2017. It's got members from the agency, water companies, and National Resources Wales, chaired by Dom Shepherd, who we'll be hearing from tomorrow. So the key aims of this group have been to improve the regulation of dry weather flow and flow to full treatment compliance at sewage works. It's about also improving flow data quality, and also supporting the development of the PR19 AMP7 flow drivers program, which Oliver referred to a minute or so ago, and to support also the development of conditions that will be used to recognise the AMP7 flow driver outputs, which will need to be included in permits. So next slide, please. So I'll just quickly talk about dry weather flow before moving on to flow to full treatment. So dry weather flow is basically it's the flow that's received. It's been defined. The definition changed over 10 years ago. So it's basically the flow that's exceeded 80% of the time, and we assess compliance with it using the flow that's exceeded 90% of the time. So it's an annual assessment. We use the total daily volumes that have been measured by driver of the flow monitors that are MCERT certified, and if the Q90 of a year's total daily volumes is bigger than the drive of the flow limit, then we say that it's exceeded its limit. But whether or not it's failed with the existing condition is subjective, because we also then have to assess whether or not the operator's taking appropriate steps, or if it's due to unusual rainfall. And so you can end up with having exceedances that might go on for a while whilst the company or the operator's carrying out appropriate steps. And it's not a clear, it's not a clear defined pass-fail condition. So next slide, please. So from 2026, we're keeping that same assessment approach the same. The monitoring will remain the same. The assessment in terms of whether or not there's been an exceedance of the drive of the flow in a year will be the same. But the difference is that if within a 5-year period you have on your third exceedance, then the drive of the flow limit has been failed. So it's a clear compliance test. There's no ambiguity. So it's the intention is that it will drive a proactive approach by the companies to avoid drive of the flow fails. So it's clear what the drive of the flow limit means. So it allows the companies to better plan, to reliance on agreeing with the agency appropriate steps if exceedances, to avoid exceedances becoming failures. So to do this, though, it involves a new condition, and that has to be included in around 3,000 permits. So they all need variant, but we've got the opportunity to do that because of the permitting of the AMP7 flow outputs, which we'll come on to shortly. So just quickly, the example I've got here, flow exceedance at Sewage Works on the 2026 data. Then if there were 2 exceedances in the preceding calendar years, 22, 23, 24, or 25, then it's a fail. So it makes drive of the flow compliance equivalent to numeric quality compliance in terms of the ease of being able to say whether a discharge has passed or failed a limit. We'll also, including that drive of the flow limit in permit conditions, we'll also be including some data quality conditions in the permit as well. Those data quality of drive of the flow monitoring data currently is in guidance, but it's going to be included in permit conditions to make the expectations clearer. So next slide, please. So why are we improving flow to full treatment? I'll move on now to flow to full treatment compliance, or flow pass forward flow compliance. So why are we improving it? Why do we want to improve it? So we want to make assessing flow to full treatment compliance routine rather than complex. So currently, checking flow to full treatment, it often requires use of data that's not been assessing FFT compliance, using monitors not installed for that purpose. And so it can be a very complex assessment to demonstrate beyond doubt that there's been a breach of flow pass forward, flow to full treatment conditions. So, and we know that there's increased scrutiny of storm discharges across the board from media, MPs, pressure groups. It's recognised that we need, as Oliver mentioned at the beginning, we need monitoring is needed to know what's spilling to storm tanks in the environment, and also to be able to check whether or not when the overflow operates, that it's whether or not it's compliant with its flow to full treatment and then other permit requirements on. So having routine monitoring of flow to full treatment, it will give us a better understanding of the impacts, potential impacts downstream of sewage works, knowing how they operate. So next slide, please. Thank you. So, team, AMP7, flow to full treatment compliance monitoring drivers. Yeah. So I'll just quickly run through these. So what the in AMP7, which runs from 2020 to 2025, there's some drivers for installing monitoring that will be used specifically to check flow to full treatment compliance. So that's at wastewater treatment works and also for what line those means there. So this is where the flow that controls from the catchment what goes forward for treatment is at a last in line overflow, which would typically be at the terminal sewage pumping station. So UMON3 is eventually currently there'll be probably eventuation monitors on discharges from the storm tanks, but UMON3 for AMP7 for flow to full treatment is to also on what goes into the storm tanks. So in addition to what we're monitoring what goes into the storm tanks, we're also monitoring under UMON4 and having an installation of flow to full treatment flow monitoring. So that monitor, those monitors, the data from those, the flow monitors and the data from the eventuation monitors will be used to check compliance with flow to full treatment settings. So the driver allows existing flow monitors that are MCERT certified for driver of the flow to be used for FFT monitoring, if it's possible, to save costs of installing new monitors. But if an existing monitor isn't good enough, then the requirement is to install a new front-end flow to full treatment monitor. There's also a driver to have investigations, UIM2. So that's where it wasn't clear whether the existing flow monitor would be able to be used for flow monitoring of FFT or not. So that driver allows investigations to go ahead and check whether or not the monitor can be used. If it can, then it will be used in AMP7. If it can't, then it will get a driver for a new monitor to be installed early in AMP7. Sorry, early AMP8. So next slide, please. So as I mentioned earlier, there's UMON3, UMON4 permitting. There's getting on for 2.5, well, nearer 3,000. There's several thousand actual AMP outputs in all for UMON3, UMON4, but they relate to getting on for 3,000 sewage works and last in line overflows that will all require permit variations. So we've produced a new permit template, which includes AMP7 flow conditions. And it's up to the agency's national permitting services and the water companies to agree permitting plans so that these AMP7 outputs can be permitted using the template, so that as well as the installations being installed and in place and being used, there are permit conditions that require them and set sort of parameters in terms of what has to be reported. So just quickly, this slide here is just, you often hear people talk about FFT, FTFT, and then flow pass forward. The permits, we all use the term flow to full treatment, FFT, but actually in storm permits, what's referred to is the flow pass forward flow. So I might use these interchangeably, FFT, flow pass forward flow, but they're essentially meaning the same thing. Because flow pass forward flow is what we're talking about here, is the rate of flow that's arriving at just sewage works from the upstream collecting system that it served, that's passed forward for treatment. Through the works. So UMON4 and UMON3 and MCERTs. So MCERTs, I think we'll probably hear more about MCERTs over today and other days, but it's a certification scheme for monitoring, and there's one for flow monitoring, I mentioned it earlier for dry weather flow monitors. This relates here to UMON4 monitors, which are measuring the flow pass forward flow. There will be a specific MCERT certification for that purpose. And so all of the UMON4 monitors will have to have MCERT certification during this AMP7 period. UMON3 monitors, they're the overflow operation monitors. There isn't a standard for that yet, but a standard is being developed. And so the intention is that those monitors that are installed in AMP7 will be MCERT certified in AMP8. That's the plan. And the reason that we have MCERT certification and why it's important is that data that's used for checking compliance, that's what the MCERT certification scheme is there for. So it's to ensure that the monitors are properly installed, right equipment, and that they're managed, operated, and maintained under an MCERT certified management system. I just would add as well that when I'm talking about UMON3, that's the EDM on the overflow operation monitoring of what goes over into the storm tanks. That MCERT standard will apply only to it's there to apply only to those overflows, not all of the EDM overflows that exist across networks and on the discharges from the storm tank, etc. Just clarify that point. So UMON4 MCERT certification. So it's up to MCERT inspectors. They will come along to look at the installation, and they're there to confirm whether or not the flow monitor can be certified to monitor flow pass forward flow. So MCERT certification for flow pass forward flow, even if it's the same flow monitor, it will be in addition to driver flow MCERT certification. And so the inspectors need to look at the installation and flows that are arriving at the works, or you need to consider return flows, return process flows. So they may come in, there may be some process flows that come in upstream of the overflow, upstream of the monitor, and they all need to be taken into account. So there may be the need for subtractions, there may be need for monitoring of the flows to be subtracted, or it may be that those flows can be just subtracted because they may be fixed. Other factors to take into account, there may be auto inhibits that mean that actually these flows won't take place when the overflows operate, so they don't need to be included or subtracted. So there's also other complexities, considerations to take into account, like the site drainage from the sewage works, storm tank returns, imported effluent. So it's quite a lot of things to consider. And there might also be, in terms of back-end flow monitors, other aspects that need to be taken into account, because it may be that a back-end meter can be used at works, or it may be that there's a lot of other added complexities that need to be taken into account, leading to higher sort of uncertainties on top of the flow monitoring uncertainties. But essentially, the MCERT requires that the flow monitor is able to measure flow pass forward, the FFT, with an uncertainty now greater than plus or minus 8% of that flow. Next slide, please. So the UM2 investigation drivers. So there are quite a lot of sites where the operator wasn't sure that an existing monitor could be used, but the intention is that where possible, there'll be a prioritisation of the use of front-end flow monitors, because they will better be able to measure and represent what's being passed forward for treatment, rather than one that's at the back end of the works. Back end of the works flow monitors might be MCERT certified for driving the flow monitoring, and perfectly good for that, but not necessarily acceptable or usable for measuring the flow that's being passed forward at the front end of the works. So If that investigation, if it shows that a front-end monitor can be used, then it must be MCERT certified and used to measure FFT within the AMP7 period. But if there's no existing flow monitor that can be used, but an existing back-end one can, again, that must be MCERT certified to measure flow-to-full treatment within AMP7. But as I said earlier, where there's no flow monitor that can be used, then that will result in an early UMON4 AMP8 front-end monitor that would be MCERT certified to monitor flow-to-full treatment. That would be as early as possible within the AMP8 period. So, after 2020. So that's where more work's needed to install a new front-end monitor. Next slide, please. So we're putting all these monitors in, or the company's putting all these monitors in, getting them MCERT certified, and what will happen? What's the reason for doing that? So permits that how do we assess compliance with flow-to-full treatment and data quality? So currently, we control flow-to-full treatment with a setting condition in permits, and that setting condition will specify the flow pass forward that has to be met before the overflow can operate due to rainfall or snowmelt. So that condition is going to stay in the permits, but there'll also be a flow-to-full treatment limit that's being developed, and that will use a routine annual assessment to assess compliance using the UMON4 MCERT FFT flow monitor data, 15-minute flow data, and the UMON3 overflow operation monitor, which will monitor and tell you when the overflow is operating. So that might be 2-minute monitoring, polling every 2 minutes to say whether it's spilling or not, or it might be monitors that say, I started spilling at this time and I've stopped spilling at that time. So that data will be pulled together, and we'll look at that in a moment. But also, there'll be data quality conditions for UMON3 overflow operation and the FFT flow monitors. And the intention is that there will be an annual compliance report that will be submitted by the companies that will show compliance against what we'll come on to in a moment. So the FFT flow pass forwards, so the limit, the intention of this is to make, as mentioned earlier with driving the flow, to make the compliance assessment more straightforward, and result in a pass-fail result. So at the moment, if you're looking at compliance with the setting, it can involve fairly complex assessment of existing data. But moving forward, the intention is to have a limit, and then if this limit is failed, then we can be confident that the FFT, that it has failed, that the limit's been breached, and that it's failed, just as we will be with the new drive with the flow condition or on numeric discharge quality limits. So we'll use the UMON3 overflow operation monitoring will show the periods that the overflow is operating, and then you'll take that 15-minute flow data whilst the overflow is operating to assess compliance, and it will involve just to allow time for the flow to rise at the monitor. The first 15-minute flow readings won't be used, and if it's a back-end flow meter, the first 2 15-minute flow readings won't be used. We can also agree there will be means of some readings being removed if there's no overflow from the storm tank and they're emptied as soon as possible, where the storm tanks have been used for like planned maintenance purposes. Next slide, please. So the limit will look like, so if 95% of these 15-minute flow readings that have been taken whilst the overflow is operating must be at or above 92% of the FFT. So the limit is allowing for the uncertainty of measurement, data quality, time for flows, passing the monitor to respond to the increase in flows from the overflow control at the front end of the work. So if the limit's breached, if there's less than 95% of these readings that are at or above 92% of the FFT, we can be confident that it's failed, that the limit's failed, that the FFT required FFT is not being passed forward when the overflow is operating. So that's how it will work. The FFT setting condition that I mentioned earlier, that will remain in permits. Along with the requirement that the overflow must only operate due to rainfall or snow melt. So this last point here, that yes, there's this requirement that 95% of the 15-minute flow reading must be at or above 92% of the FFT, but that's not to say that you can just operate the overflow and set it at 93% of FFT and think, yeah, there I am, I've complied, because the setting condition remains, and the expectation is that the uncertainty that you have is plus or minus either side of the FFT, not systemically below 100% of the FFT. So next slide, please. So this is if the overflow operates in short bursts, well, we're using 15-minute flow data based on the periods where the overflow is operating and discounting the first reading. So yeah, if you've got if you've got overflows that operate for more than 15 minutes, going and extending onwards, you'll have 15-minute flow readings that will go into the compliance assessment. But if you've got if it turns out that the way your overflow operates, for example, if it's a pump storm overflow, it might operate on and off such that you don't get long enough periods of operation to get the 15-minute flow readings to assess compliance. So we've said there that the human flow FFT flow monitoring should be 2 minutes, every 2 minutes, and we're going to assess down the line whether or not there's a need to move to 2-minute flow monitoring in unpaid if needed. Next slide, please. And this is just a rough example of the lines represent from the left there the period when the overflow starts to operate, and then each line is actually a 15-minute reading of flow data as the overflow continues. Some of those you can see go on for longer than 6 hours. And so what this is showing that depending on the conditions before an overflow starts to operate, the flow that the monitor's reading it can be relatively low if you get flown from a following dry period, or it can already be quite high if it's already been wet before the period beforehand. But what you can see there is a sort of dogleg at the front that's taking time for this flow monitor, for the flow passing the flow monitor to sort of be the flow that was passed forward by the overflow that's controlling flows into the works. And so that's why we knock off the first 15-minute readings in the assessment, or 30-minute readings if it's back end here. It looks like it's taking around 30 minutes for some of these flows to sort of reach the overflow operation level. So then going across there, you can see that the flows are sort of either side of 100% of the FFT. And you can see also that there's down at the bottom there at 40 or 45%, there's a line that potentially could be, a discharge to the storm tank because of maintenance. And it might be that, and assuming that the overflow didn't result in spill from the storm tank and the storm tank was emptied, and those readings might be discounted from that 95%. The readings must be at or above 92% of the FFT assessment. So I don't, some of those blips there, potentially data errors, something's not quite right there. That's just an example of what data might look like if plotted in that fashion. Data quality conditions, as I said, we're putting in the conditions in the permit that specify that you shouldn't have more than 14 consecutive days in the calendar year where you haven't got good flow data or good overflow operation data, and then 37 days in total where you haven't got both of those good data, both overflow operation and flow monitoring, FFT flow monitoring data. So those quality conditions will be actually in the permit. Next one, please. And so at the end of the year, there'll be an annual summary report submission by the operator for each of these sites. So it will give you the percent of flow readings that were at or above 92% of the FFT whilst the overflow was operating. So if it's 95% or more, that's a pass. If it's less than 95, it's a fail. The max consecutive days, not good flow data, not good overflow operation data. If that's more than 14 consecutive days in either of those cases, then that's a fail of that data quality condition. Similarly, the number of days with not good flow and good overflow, if that's more than 37, again, that's a fail of the quality condition. So other things like for indicative purposes to understand what's happening and check there's no other issues, we also have duration of overflow operation, frequency of overflow operation, and then other stats such as annual mean, median flow, whilst the overflow of the readings whilst the overflow is operating, to be clear that yes, the flow monitoring is showing that the setting condition is actually being met, as well as the FFT limit. So the data is to be submitted to the agency annually by the operators, just as the driver the flow data is at the moment. So just the last slide, please. So yeah, the benefits of improving regulation. So it moves the regulatory focus to flow and effluent load, not just discharge quality. It makes driver the flow and FFT compliance assessment more straightforward and simpler, more straightforward and routine, and it sort of matches with the sort of zeitgeist at the moment and ongoing of the increased challenge and public awareness of the impact of storm discharges, and in terms of driving the flow, and the companies will need to plan ahead to avoid driving the flow fails and also ensure that there aren't FFT fails as well. So that bring a bright light to shine on the actual flow to full treatment compliance and driving the spills and sewage work. So that's the sort of from the agency's perspective of the benefits of improving regulation. So that's a whistle-stop tour through flow regulation and where we're going over the coming years.
Thank you very much, Pete. Good. That's a great introduction to what is going on with flow. I know dry weather flow, about 2010, I think, had this sort of big update. I think we're now moving to FFT. I mean, do you think, to be fair, do you think FFT's really been properly understood within the industry? I certainly know when I was a design engineer, FFT was treated as a maximum, which isn't the case. It's a minimum of a works must treat. do you think there's part of the problem is that misconception that we've had over the years?
Yeah, potentially. I mean, it's like I said at the end there that we're shining a light on FFT. I mean, it's we as an organisation we focused on data, discharge quality. So yes, it's harder for us and the operators to sort of like routinely understand FFT. So yes, it's not been in the operator's face or our face as to whether or not a subject is passing forward the right flow. So it's if companies may sort of because they're not having it in their face, might have sort of ignored the issue and assumed that things were okay when they might not be.
Yeah, from my point of view, it's always the message. I've worked for a few water companies now, directly and a few indirectly. The message has always been compliance is king, and that's meant quality compliance. And I think in some ways, flow management, especially with all the other issues at the minute, flow management is becoming more and more important. Quick question from Mark Swain. Half a question, half an observation. In 2019, we had a significant amount of rainfall. In 2020 and part of 2021, many sites, especially the rural site treatment works, have seen increased flows as basic due to COVID and more people staying at home. What the question there is, what's a normal year for DWF these days?
Well, a good point. I mean, but if DWF does change, then it would have to change, wouldn't it? I guess ultimately, if flows are increasing at works, because genuinely there has been a change in that there are more people, there's more load actually going to the works now. It would have to, that would have to be reflected ultimately. We don't know how things are going to stabilise, do we? And I mean, the new condition, yes, it moves away from assessing on an annual basis whether or not appropriate steps are being taken, but it does allow there to be two exceedances that might be due to things that you're not, that are outside the control of the operator. So it's not in the operator's interest to think, I've got two exceedancies that I can wait for them and then do something about it, because those exceedancies, like you say, might be due to they're there for unexpected events.
Yeah, and to be honest, I mean, there's always the safety factor that was built into DWF between the Q80 and the Q90, which has always been there. So there is a safety factor there, but it's well worth. To be honest, I think from my point of view, the 3 and 5 approach and the Q80 Q90 it works quite well. I think that's a good part of it, and I think bringing forward flow management as a bring its importance forward is very, very important right now, especially with everything that's going on. On that note, I think it's probably worth bringing in Cathy Boorer of Thames Water, who's going to look at FFT compliance in terms of a water company. I think probably the difficulties that we face, but I'll let Cathy talk about that. Cathy, do you want to take over?
Yeah. Hi there, everyone. So yes, as Oliver said, my name is Cathy Boorer. I am from Thames Water, so I work within the kind of engineering and asset function, mainly in the environmental compliance space. So I'm the flow and EDM lead for Thames Water. As Oliver said, I think I've definitely seen my role expand from just a flow quality specialist keeping the MCerts program ticking over to now as the focus and attention is on flow, and we've realized just how important it is to get things right, to absolutely how my responsibilities have expanded. We've now got a whole team involved, and it's really looking like this is something that we really want to focus and want to make our priority. So if we just move to the next slide, please. Just a quick overview about Thames Water. So Thames Water, we sit serving kind of London and the Thames Valley area. We've got kind of 15 million or so customers that we serve. So a very broad scope and a lot of customers to serve and to process. And we're going from teeny tiny little sewage treatment works in the middle of nowhere, serving a very, very low population, right the way up to kind of Beckton, one of our London sites that has a population of 2.5 million or so. So we really do see that kind of both broad ends of the spectrum in terms of the challenges that we're facing and what we're looking at. So if we just move to the next slide. Yep. So as kind of, I'm sure a lot of people are aware, the fact that you've come along to this session is just the interest in flow management and flow to treatment and storm discharges just has absolutely exploded over the last kind of 6 months to a year. We are seeing so much more media focus on it. We are seeing, we've had the Panorama documentaries, we've had other documentaries, all really, really, high quality media focus on it. Some really passionate stakeholders. I can't speak for all areas, but certainly in Thames Valley, we've got some really, really interested stakeholder groups that are from, our Anglian trust, from the angling point of view, from sailing, from open water swimming, because that has exploded over COVID. We're seeing, paddleboarders, we're seeing everyone just being really, really interested in their local environment, in their local rivers. And they are quite rightly quite upset with what they perceive to be a decline in quality, in an impact on their watercourses, and they want to understand why. And they are challenging us as a water company, do better. What are you doing about it? We're seeing this impact. Is it from you? What are you going to do to stop it? And that's what we're seeing, a lot of interest from our stakeholders, a lot of interest from the media. We've had the environment bill that's gone all the way up. Usually these things take a long time, and I think all of that attention and that passion from our stakeholder groups has really seen that in that addition to the environment bill of specifically about water quality and things like that going into that. And I think actually we've got the Environmental Audit Committee is sitting today listening to evidence from CEOs from water companies, including Thames Water, and I think it really just goes to show how interested everyone is in this subject and what we as water companies are doing about it. So if we go to the next slide, I can flash up what we are doing about it. Thames Water's position certainly is that, environmental harm, environmental damage is completely unacceptable. We don't want to be doing that. But first of all, I think we need to take a step back and understand, what is it that we're doing? What is our impact? What is happening in our environment? And do we have a part to play in that? So we've got various monitoring investment schemes that we've already been doing over the course of last AMP and this AMP, the kind of asset management period. So Pete covered some of these drivers, some of these focuses in his presentation very, very well. So on the left, kind of in the blue, we've got the kind of the monitoring schemes, and then on the right, we've kind of got the what we're doing about it schemes. And as you can see, it's very, very heavily focused at the moment on just getting that monitoring in place, understanding what are we doing, how often are we doing it, where are we doing it, so we can try and really understand what is actually going on. So we've moved from, as Pete said, we've pretty much had various monitors in, but from a regulatory point of view, we've pretty much just had the dry weather flow, the final effluent. What are we finally treating and discharging into our watercourses? And now over last AMP and this AMP, we're really wanting to understand, okay, not just what are we discharging from a final effluent point of view, but what are we discharging from a storm effluent point of view? So there's various drivers with that. EDM1 and EDM2 from last AMP, so we put those in to try and monitor what are we actually discharging from our storm overflows into the environment. And we're getting some really good data back from those now, really starting to understand where the problem hotspots are, what are we doing, how often are we doing it. Flow 3 and Flow 4, those are flow drivers. So those were to install more flow monitoring in various places. So Flow 4 in particular was a kind of prelude to what we're seeing this AMP. So it was targeting certain areas and trying to put some flow to treatment, flow monitoring in those areas. And then moving on to this AMP in investment, we've got the WWEM3, WWEM4 and WWEM2 drivers, which, as Pete said, the WWEM3 driver is to put monitors on not just our overflows to the environment, but actually the overflow to our storm storage on our sites. And that very much works in conjunction with the WWEM4 or WWEM2 drivers, which is to understand actually flow monitoring at the point of overflow. What are we treating incoming from the network new? Are we meeting our obligations there? And I'll go into a little more detail later on about why that's so important to have those different monitoring points. And then again, on the right, as I say, in terms of regulatory drivers, we've got the UINV driver, which is our SOAF program, our Storm Overflow Assessment Framework. That's identifying using data from our EDM1 and EDM2s that went in last AMP, understanding where are we spilling to an unacceptable high amount. What, are we investigating that? Are we understanding the reasons why? Cost benefit analysis, what can we do to try and reduce those spills? And the outcomes of those investigations will feed very much into our AMP8 investment program, and get delivered there. Although obviously if there are any easy wins, we will be implementing them as soon as possible. We don't want to be waiting around. And then WIMP5 and WIMP6 drivers are all about, can we put more investment into our sewage treatment works to, we might be meeting our flow to treatment value, for example, but actually is that flow to treatment value appropriate now? Have we had more growth in the area? Do we need to increase what we are treating as a flow to treatment value before we then subsequently discharge to storm? And then the WIMP6 driver is all about increasing the size of storm tanks on our sites. So it's understanding, okay, if we are discharging, if we are taking too much flow into our works, we're discharging to our storm tanks. Let's make those storm tanks bigger so that we've then got the opportunity, okay, can we then, if we're capturing more in our storm tanks, we're not having to discharge as much into the environment. Potentially we've got the ability there to store it in our storm tanks and then return it back to our works, once that storm event has passed. So then we're treating more and we're not discharging as much partially treated sewage into the environment there. So as well as the regulatory drivers, we have also got our the non-regulatory stuff that we're doing. We're not just doing the stuff that's on the WINEP, on the National Environment Programme. I think Tideway Tunnel, from a Thames Water point of view, that's probably our biggest investment, or probably our biggest known about investment. I won't talk about that as much now because we're talking about flow to treatment, and that's more focusing on the kind of the network sites in the London area. But we're also doing a lot of other investment in terms of identifying where are we non-compliant with flow to treatment. What can we do about it? We're engaging with the Environment Agency, with our local EA offices to understand, where are we falling down? What can we do? Are there some quick wins in terms of, okay, it's just a matter of putting in some more, flow regulation and a penstock tweak or something like that, right up into, okay, this needs a much bigger investment, and let's get some money together and get a program together to make those changes and make those fixes. So we are doing a lot now to understand what our impact is on the environment and to try and reduce that as much as possible within this AMP, within the next 3 to 4 years. So we go to the next slide, please. All of those monitoring schemes, you can see what by the end of this AMP might be possible monitoring on a sewage treatment works, and I'll focus on sewage treatment works because we're looking at flow to treatment here. So as you can see, we've kind of got the inlet, we've got the final effluent, and then we've got a storm tank on a potential sewage treatment works. So by the end of this AMP, we might have, via the WWEM4 driver, a flow to treatment flow meter that is MCERT certified, that is calibrated, that is assessed independently, that has a management system in terms of maintenance and data integrity and data quality. We will have a final effluent flow meter that we've probably had for years and years and years. That again will be an MCERT certified meter, so we'll have its own management system and independent certification and everything like that. We will have the EGM to the environment, which we've already installed in most cases. So that will be not MCERT certified, but certainly we want to make sure we have the most accurate data we can. So possibly a little bit masochistically, we are implementing a management system in terms of maintenance and data integrity and data quality, because we want to make sure that we're reporting accurate data. And then via the WWEM13 driver, we will have the spill to storm monitor, which, although again won't need MCERT certification until AMP8, again we want to make sure that we are measuring accurately and have full confidence in our data. So you can see on an average sewage treatment works, we might have 4 points, 4 streams of data coming in. As I'm sure many people on this call know, it's not as simple as what goes in, 1 point in, 1 point out. So in some cases, you might have multiple flow meters making up the flow to treatment flow meter flow data, and multiple flow meters making up the final effluent flow data. So that is a lot of data to keep track of, to make sure is accurate, to be monitoring, to be maintaining. This is, you know, I'm sitting here as a water company and we're realizing just how much this is going to explode. It's not just sticking the monitors in. That doesn't work. If you stick a monitor in and ignore it, you're going to get rubbish data. So you need to be looking at it. You need to be looking at the data, understanding what it's doing. You need to be making sure that there's maintenance going on. You know, we're seeing instances of where we're investigating spills to the environment, in inverted commas, and, you know, we get there, we've got a completely bone dry storm tank, and then you look and it's got a load of cobwebs under it, and you know, everything like that, and that's what's causing the spills. Or you've got vegetation waving under it. So then you've got, you know, you realize, okay, actually the monthly check that we put in originally does not work at this site. This needs a lot of attention, and especially when you think, you know, summer months you get more vegetation growth and things like that. So having accurate data is step one for us. We can't do millions, billions of pounds worth of investment until we are happy and confident with the data we've got. So we move on to the next slide, please. You can see some of the things we're doing to try and make sure that we do have as accurate data as possible and understand what we're doing. So here we've got a dashboard, and it is showing us for a site what the rainfall's doing in the area, and that's taken from open source Environment Agency rain gauges. We've got in the middle, we've got what our EDM is saying. So that's our EDM to the environment. So that is essentially just level data. And then when the yellow gets over the red line, that is showing that that's a spill. That's, you know, over spilling the weir threshold. And then on the bottom, we have flow data coming from our final effluent MCERT's flow meter, just to give an idea of what we're doing. And for all of the regulators kind of peering at this, don't worry, I've carefully selected a site that is squeaky clean and fully compliant. So I'm not. So yes, and I think as we were looking at this, originally we created this dashboard with a thought to just EDMs and verifying and validating EDMs. And so our thought was, well, we'll bring in some flow data and we'll bring in the rainfall data, because then we know, well, okay, if we're getting some data from the EDM and it says it's had a discharge and it's happened while it's raining and the flow's gone up, well, that's probably an indication that that spill was genuine, that was accurate. But of course, we then started thinking, well, actually, now we can have a really good indication of, are we compliant, as well as is the monitor working. So now we're looking at things and we're implementing, and we're going, okay, can we, you know, on a monthly basis, let's take the top 10 spillers in each of our operational areas, and we are now doing an eyeball check, and we're looking at not just are we happy those spills genuine, but we're also looking and giving a kind of an indication of, okay, well, did that spill also happen when there was rainfall in the area? And did that spill also happen when our flow was reaching its flow to treatment level? And those are the sorts of checks we can already do with the data we have. There are some caveats with that. Obviously, this is a very manual process. It's kind of eyeballing it. It's relying on individual judgment, although my team are fantastic. I do trust their judgment, but it's not very helpful in terms of understanding, okay, as a whole, across our entire estate, what's our risk? What are our sites doing? So if we move to the next slide, please. We have also implemented some assessments based on the methodology that UCWER came up with a few years ago. This was kind of trying to get an understanding of, okay, what is the kind of uncertainty due to flow, using final effluent flow meters and on that spill to the environment, because that's not necessarily what your flow to treatment's doing. If you've got a flow meter on a back end of a works and it's after a reed bed, after some filter beds, after sand filters in some cases, that is going to really stretch out your data, and what is saying at the back end isn't necessarily going to be very representative of what's happening at the front end. So can we do some statistical analysis to try and kind of smooth out those uncertainties, try and get the best idea we can? The idea is, okay, if you have a spill that goes on long enough, flow will kind of plateau through the works, etc., etc. So this is what we kind of tried to do, and in some cases worked really well. Again, this is a squeaky clean compliant works. This statistical analysis, if you look at this and try and think of it as this is the profile of an average spill from this works. So as you go along the graph, that's kind of the longer a spill goes on average. The purple, as you can see, that is every data point we have from an EDM, every spill data point we have. So as you can see, we have much more spills from this site that are the shorter length spills. And as the length of the spill goes on, towards the end, you've got like one spill that's gone on for 8,000 minutes or whatever it is. So then you've got lots of statistical stuff going on, working out what the 25th percentile is, what the 50th percentile is, what the 75th percentile is of all of the flow that's going through the works while the overflow is operating. So that's various things there. And then you've got a line which is what is your flow to treatment value. That's 100% of your flow to treatment. And we want to see, as you can see, all of those lines, all of that flow on average is above our flow to treatment figure. Beautiful, brilliant, compliant site. In fact, this site is so compliant, it actually has a driver to increase its flow to treatment. And if we move to the next slide, please, you can see where this methodology falls down a little bit with us and with some of our sites. Because now what you're seeing is you could look at that assessment and kind of go, well, okay, what's happening here is that flow at the start of a spill is not meeting its flow to treatment, and it's getting to the flow to treatment towards the middle and end of the spill, but that site is delaying, it's spilling early, it's taking 100 minutes to get to its flow to treatment value on average. But then you need to think, well, actually, where's this data coming from? If it is from a back-end flow meter, what is the setup of the flow on that site? Where is that? What's happening? What else is happening? What other returns are going on in order to impact that flow data? So in some cases, it's very, very easy. What goes in pretty much is what comes out, and you can match that up very, very nicely, and there's a very short delay. But are we confident what's going on? So this now is like, okay, it's not as simple now. It is now we need to figure out, right, is that just the delay of what's coming through the works? Is that actually, no, this site has a genuine problem and it is spilling early? And from our point of view, we're potentially going to be spending millions of pounds at this site's worth of investment if we think it has a problem that needs to be fixed. So this is a site where we'd look at and go, okay, actually, before we can make an 100% pronouncement of what the flow to treatment compliance at this site is, I think to be comfortable, we need a flow meter actually on the front end at that point of storm separation, at the flow at the flow to treatment, that is M-certed, that is is accredited, is calibrated, is of a certain quality that we are confident in, before we to understand exactly what we're doing and exactly what the issue is. So this is a site where we really do need that flow to treatment M-certs meter, and it does benefit from that, and it shows why it is so important to not just have that final effluent flow meter sometimes, but also you need that UMON 4 driver, you need that flow to treatment flow meter as well. And that's why often when I am asked, Cathy, what's your flow to treatment compliance across your estate? I do this sometimes, and I am very uncomfortable with giving a figure. And that's not because I don't want to be open and honest. That is because I am facing however many sites like this. We've got some really easy ones that I can make that, and I can be confident in what I'm saying. And then we've got sites like this where I'm like, well, it might be this, it might be that, we're not sure. And that's what I'm seeing when I'm looking at the data, and that's why I'm so excited about the WWEM3 and WWEM4 drivers coming in, because that removes all of that uncertainty, because it is actually at that point of overflow, at that point the storm tanks start filling. You can't argue with that, of what's happening there. So we move on to the next slide, please. Just talking about some of the kind of challenges we've looked at. As I say, data accuracy is a constant thorn in my side. I have thousands of flow meters and EDMs, and I've got hundreds more coming in, thousands more coming in of the WWEM3 and WWEM4 monitors. That is a lot of meters, a lot of data streams. As Pete said, we've got the new WWEM3 spill to storm overflow monitors are going to be 2-minute data. So I've got 15-minute data here, 2-minute data here to reconcile. I've got, flow meters over here, flow meters there, flow meters there, flow meters there. It's a lot to keep track of. And keeping that data accuracy going, making sure that the maintenance is being undertaken correctly, reactive maintenance, on a sewage treatment works, it's difficult enough. And then you consider when you go out into the network and you've got to get traffic management and try and convince Transport for London that you need to shut down a major artery in London because we need to access a manhole for an EDM. It's all fun and games, but it really is a challenge, just maintaining just the data accuracy and that data integrity before we even start on anything else. It's so important. As I say, other challenges we're facing, I said about the passion of the stakeholder groups we're getting, through the environmental information request process, under the Freedom of Information Act, anyone can request any environmental data from us, and they do. We get a lot of requests for data from stakeholders, from customers, from regulators, from the Environment Agency. Everyone now knows we have this data and wants it so they can see for themselves what they're doing, which is great. I'm so happy. We do have a lot of really interested and passionate stakeholder groups that want to work with us, but it's a lot. It's a lot of requests, and a lot of what we're doing at the moment is really trying to understand how we can manage that and how we can make that process easier for everyone. Because I'm sure stakeholder groups don't want to have to email us every time they want a bit of data and then wait 30 days to get it back, and then it's wrong, and then it's all this back and forth. Other challenges we're facing, the evolving regulation. As Pete said, there's a lot of really exciting stuff going on at the moment in terms of understanding what we need to do and how we're going to do it and how we best capture that, and making sure that every water company is treated the same and is providing the same data. There is a lot going on in that space at the moment, at kind of all levels. And it's just trying to make sure that we keep on top of that, we understand that, and that we make sure we know what's going on. And that we can plan and budget for it as well. That's quite important. And then, linking in with the data requests, it's the data infrastructure. It's just making sure we understand, how much extra data we do have coming in. How do we manage that? How do we calculate compliance from that? How do we communicate that out? We can look at some really fantastic monitors and meters, and they're all using the Internet of Things and MQTT brokers and everything like that, and then you try and match that into our SCADA system that's however many decades old, that really isn't designed to be compatible. I think we have got ahead of ourselves slightly with some of our WWEM3 monitors, and we're having to use a completely different reporting system at the moment until we can get that integrated into our full systems. But it's good because it challenges us to be better, to improve, to constantly be looking at the best way of understanding this data and capturing this data. Opportunities we have, it's, as I say, it's such a greater knowledge and understanding of our assets. It's sites that, I think everyone's got sites where there's a problem, and then you have sites where you're like, oh, okay, actually that's an issue there. what is that issue doing? As I say, is the issue that it's not meeting flow to treatment entirely? Is it that it's taking a while to get there? Is it getting there but not holding it? And understanding that it's really helping us understand and target our investment needs and what we can do to do the best thing possible in order to fix what needs fixing. As I say, driving technological innovation, it really is. We are moving from, my own personal understanding from, has gone from being very, very basic, and the data stream sits there, and please don't ask me any further about what it does, and it does something there, to really understanding, right, what is the difference between the 2G monitors we have out in the network and the Internet of Things and Bluetooth, and someone can just go up and do it without needing to even access the manhole, and it's brilliant. And we have been working with some really fantastic contractors and some fantastic equipment manufacturers as well, to really work with us to understand actually what can we do to do the best thing possible, not just to meet the current regulatory need, but looking forward to that. For example, the AMP8 MCerts coming in, we don't want to put something in that we're going to need to rip out in 4 years. How can we work with everyone to make sure that we're future proofing as much as possible? Working in partnership with stakeholders, I said a lot about our passionate stakeholder groups, and they really they're really protective of their local environment, and we are doing some fantastic things at the moment in terms of understanding that, and the citizen science that we are getting. We can't get out all the time, but actually we've got people that are willing and able and are really, really intelligent people that can go out and can take some samples and can give them to us, and we can understand so much more about what's going on. It really has opened up that dialogue so much more, this data. And of course, really, really importantly, reducing and preventing environmental impact. I am an environmental scientist by heart. That is my passion. I don't want to see, tampons and toilet paper and things in our environment. I don't want to see that. I want to do better, and I really want to, the environment to be improved by this. And I think some of the things we're working on, I can really, really see that we are going to make an active difference and an active improvement to that local environment. And I'm so excited about that. And then last, real-time data. That is what everyone wants to see. That is what everyone wants to do. We are away from that. I refer to all of my concerns about data accuracy, and I do not want to be putting data up on a website saying we're spilling if it turns out it's a bit of vegetation that got caught under the sensor. But we are moving there slowly. We are looking into it, and that's going to really give some exciting stuff as well for us. So that is it from me. So thank you very much for listening. Hope that gives a bit of an overview, whistle-stop tour of some of the challenges we're facing and what we're doing about it.
Thank you very much, Cathy. That's absolutely fascinating. I must admit, by my own count, I think one of the challenges, if you bring in UMON4, a final effluent flow meter, UMON3, and a EDM out the storm tank, nationally you're talking around about 500 million pieces of data every year. And I think, and that's at 15-minute values. If we go to 2, then we're talking 3 or 4 billion pieces of data a year nationally. And I think this is where, in some ways, one of the mammoth tasks is that data management. And it's staggering the amount of data that we will be collecting from 4 instruments per treatment works. But I think that, as you've highlighted very strongly, I think the value of that data is huge. I know what sort of, it's going to come up in our next session, but what are some of the challenges on sort of data management that you have?
I think for us, it is that understanding, and it's the data comparison, and it's understanding, okay, the new flow to treatment requirement, for example, it's as Pete was saying, it's that 95% of your data while the overflow is operating should be above 92% of FFT, and then it's, well, actually it shouldn't be 92% of FFT, it should be 100% of FFT. And it's just making sure that you have all of that data in the right place. And it is a lot of processing power. I came into this quite naively a couple of years ago, and I was like, well, Excel spreadsheet, put some formulas in there and job done. No, it fell over immediately. So it's understanding we've got so much data, so much processing needed. It's picking out there's bits of suspect data so that you're not making an assessment on something where you knew there was just a log sitting under the monitor for however long. It's understanding how much data we've got coming in, making sure we've got the right processing power and that we are understanding it in the right way and interpreting it in the right way, because that's so important.
It is that data quality, as you said. I've been a champion of data quality for a number of years now, and having trawled through, I don't know how much 15-minute data is just going, well, that's a spurious caused by a telemetry blip, or that's caused by this or that, or that data cleansing is extreme. And when you're talking 500 million pieces of data nationally every year, that challenge alone is massive, absolutely massive. So, but I think what we can get from that is there's a huge amount of value in this data, but turning that into information, very, very difficult. And I absolutely love the dashboard you had there. Really, really like that. So at that, I think we've come to the end of this first session. I've programmed in a 15-minute comfort break for everyone. So hopefully I will see you all in 15 minutes, where we will be talking about managing the data and that 500 million pieces of data a year. We're going to have George Heywood of Ovarro, Ronnie Bains, and a colleague of his talking about managing the data, and Sam Green from Southern Water. So I will see you all in about 15 minutes. Thank you very much. Welcome back, everyone, to the second session of the Virtual Flow Forum. In this session, in the last session, we heard Cathy Boorer talking about data quality and its importance. And we also ended the last session talking about managing data. I know it's a massive issue in the water industry. We've got an absolute flood of data coming towards us, and managing data is going to be more and more important. So this whole session is going to be a discussion with George Heywood of Ovarro, Ronnie Bains of Seeq, and Darren Steele, as well as Sam Green of Southern Water. And we're going to talk about the challenges that the water companies are going to have in managing data, the value of that data, and how, with the solutions that are on the market right now, we can manage the data to get that insight that we need that will help with pollutions, that will help with flow management through the wastewater system. So at that, I'm going to introduce our first speaker for this session, who's George Heywood of Ovarro. George has had a very, very long experience within the water industry. I know George did quite a lot of the work on DWF and the Q80 work, as well as I work with George on the UPWEM project on FFT. And George is going to talk about a rough guide to flow data validation. So if you want to take it away, George.
Great. Thanks, Oliver. Thanks for having me in the presentation today. It's really good, and morning, everyone. So Ovarro, you probably know, is a company that provides monitoring and control software and hardware for the water industry and other industries, and we also do quite a lot of analytics based on those data to give extra value to them. And as Oliver's been saying, one of the areas that I've been particularly involved in over the years is analytics on wastewater flow data and also EDM data. So we're going to start off this session with some quite a kind of technical presentation. No apologies for that. I hope you enjoy it, about flow data validation. So I press my clicker. So what does validation mean? It's the act of checking or proving the validity or accuracy of something, according to the dictionary. So why do we need to validate flow data? And a few reasons here. So first of all, we need it because we do need to do that because so that we can exclude invalid data from an important calculation. And we've been hearing a lot already this morning about compliance assessment, and that's probably the most important calculation, but also planning and design calculations. We need to make sure that those are not being polluted by invalid data. And then secondly, so that we can fix a problem with the measurement, we can find out that something is wrong, and we can go out there and fix it so that we can collect better data in the future. And then thirdly, so that we can react quickly to an event of concern. So there might be something real going on that is causing this unusual data that we're seeing, and we want to be able to react to that. And that's probably what we would call anomaly detection. So it's not so much validation, but there is a kind of grey area between validating data and identifying something real that is going on, that is unusual. So what kind of things can go wrong with flow data? So first of all, there can be a problem with the measurement structure, an obstruction in the weir maybe. The sensor might be pointing in the wrong direction, leading to constant values in the data. The monitor might be set up incorrectly with incorrect range settings, and that can lead to truncated high values or indeed truncated low values, and it can also lead to discretization in the data, and we'll look at that in a few minutes. There can be changes in calibration for better or for worse that can lead to a kind of step change in the data that we're observing. There can be a loss of power or communications, or finally there could be a real world problem, a real world event, nothing to do with the monitoring, but to do with the process or that the flow's arriving, and we need to know about that as well. So the flow data is an example of time series data. It's a number of data points collected over time at a regular interval. And there's a number of different types of validation that you can do on these kind of data. And I'm going to look at each one of these just now and with some examples. So first of all, obviously, there can be missing values, nothing arriving at all in the signal. Secondly, there can be outliers, unusually high or low values that we need to identify. So sometimes there can be near constant values, so not exactly constant, but quite close to being constant, perhaps. And this could be the sensor pointing in the wrong direction, maybe, or pointing at an obstruction. There's that discretization that I've mentioned, and then step changes in calibration, and then finally the summary data that we're deriving from the time series data. These might be the daily values being derived from the 15-minute values. We need to identify invalid data in those data as well. So okay, let's start with the outliers one, and there's a number of ways that we can identify outliers in time series data, and we'll start off with the most simple and then work on to something a bit more sophisticated. So obviously we could have constant thresholds, high and low thresholds, and whenever a number is above those thresholds or below, then we invalidate that data point. But the problem with that is that they need to be set up individually for each monitor, and they might not. The appropriate thresholds that we would want to set might change over time, and so we have to keep on maintaining the thresholds, and that's quite a workload. So a step up from that is to have self-calibrating or adaptive thresholds that respond to changes in the signal in an appropriate way. And and here's an example of one of those that we've used with 15-minute flow data. So we would invalidate 15-minute flows that are less than 60% of the second percentile of the valid 15-minute flows. So we're using a a percentile value at the bottom of the distribution, and we're saying if you're lower than 60% of that value, then you're too low, and that's very unlikely to be a real flow data point. And then finally, we can have some kind of smart thresholds that not only adapt slowly over time, but are able to see what is normal within the daily changes in flow data that you might expect. So, and here's an example of that on the right-hand side there. So the yellow points are the data, and then the blue dotted lines could be smart thresholds that could be applied. And there's a number of different ways of generating these. You can, the first two there are univariate and multivariate time series forecasting methods. So the difference between those is that the univariate methods only use the flow data themselves. These are good at spotting things that are out of the ordinary in the dry weather diurnal profile, but they won't be able to respond to a rainfall event occurring. But then the multivariate methods, these can use a rainfall signal as well, and they can allow the upper boundary there to flex upwards in the event of a rainfall event. And then perhaps the most sophisticated on the list there, the third one, is machine learning approaches such as artificial neural networks. And quite a few companies are beginning to apply these to identify anomalies in wastewater flow and level data. And it's an approach that can be used for validation as well. So, okay, so that was outliers. What about near constant values? So an example there of that on the right-hand side, we've got some normal dry weather diurnal changes on the left, and then there's a rainfall event, and then at the end of that event, something goes wrong, and we see this kind of flat area of near constant flow values, and that's not valid data. The way that we usually detect this is by calculating the coefficient of variation on a rolling basis, and that's the standard deviation divided by the mean. Sorry. There we go. So my clicker is being a little bit slow to respond. That's it. So, for example, where there are 5 consecutive data points that have got a coefficient of variation of less than 0.003, we tend to use 2 different methods in parallel here. So we use that one, and then we also look for 20 consecutive data points with a coefficient of variation of less than 0.015. These are, you might want to choose your own values here, but these are ones that we found to work well for wastewater treatment flow data. So do go ahead and copy them if you want to. Now, obviously, the thing you've got to watch out for here is that there might be near constant flows because of the effect of the storm overflow weir during a long rainfall event. So we need to make sure that we're not invalidating those flows at that weir level. So we use this third bullet here so anything that is greater than 95% of the 95th percentile of the valid flows, we do not invalidate those data under the above rule. Okay, so discretization I mentioned, and on the right there's an example of what you might see if the data are suffering discretization. So for this graph, I've put some blue dots on the data points just so it's a bit easier to see. And you can see that we're not getting a full continuous range of flows being recorded. Only certain numbers it's like the monitor can only record certain values. And in this case, there are only 10 different values being recorded. and this can be caused by incorrect range settings on the monitor, or perhaps incorrectly sized monitoring equipment. And what we would do here is to invalidate data where there are fewer unique values than would normally be expected. So, for example, it might invalidate days on which the number of distinct flow values is less than 20. Ideally, you'd want more than 50 distinct values to be sure that you're getting a reasonable precision in the flow monitoring. Okay, and the next one here, validating step changes in calibration. So if there's been a change in calibration of the monitor, and that's leading to a step change in the flows that are being recorded, then the period, either the period before the step change or the period after, is likely to be wrong, and hopefully it's the period before the step change. So we can do that by, again, applying one of these time series models. I'll just show you an example of that. So here's some flow data, and you can see that the diurnal profiles to the left are a little bit lower than those to the right on the graph there. And so what we do is we create a time series model that is trying to reproduce these data, and that's the black line on the graph. And you can see it's fitting quite well to the left-hand side, but then you begin to get a divergence after the change in calibration. And so when we calculate the error between the real data and that model, and that's the red line on the chart there, and it's plotted against the right-hand axis. And you can see that the error is centered quite tightly around the zero line, horizontal line there on the left-hand side, but on the right-hand side it goes up to show a systematic positive error. And if we just put a couple of, that comes out more clearly there if we apply these horizontal lines in red. And what you can do is you can use a technique like QSUM to identify the step change, and then use that perhaps to invalidate the data prior to the step change. And then finally, invalid summary data. So far I've been talking about the validation of the 15-minute data, but often we're wanting to calculate daily summary values. Certainly we would be doing that for calculating dry weather flow. So what should we do when we're calculating these daily values? What should we do about the invalid 15-minute values? So what we tend to do here is to set a threshold whereby we would invalidate daily values that have got fewer than a certain number of valid 15-minute values, and a number we've tended to apply here is 92. So if you've got 92 out of 96 valid 15-minute values, then you can calculate a valid daily value, and then we would often also go back and invalidate all of the 15-minute flows on those invalid days. So having done the validation, sometimes we find that you would need to fill in gaps in the data where data have had to be removed because they were invalid. There are occasions when we do need a complete data series. And there's a number of approaches for doing this. So if you just got a very short gap, maybe just 2 or 3 15-minute values, then you could do that with just applying a linear interpolation, kind of joining the dots in a straight line to infer values in the gap. If you've got a larger gap in dry weather, then a time series modeling approach like ARIMA, again, you could use to fill in data in that gap. And if it's in wet weather, then you might need to go to something more sophisticated that can model those changes that are being driven by the rainfall. And in all of these, you might need to truncate the result to reflect the effect of the storm we are setting, because the models may not adequately do that. Okay, so just in summary, this is what we've looked at. We've gone through a few different approaches for validating flow data, and I hope that's been useful. I think I guess it's something that a lot of you have had to think about in the past, and be interesting to hear your thoughts in the discussion. Oliver.
I must admit, the vast majority of those I've come up against. The best one is certainly with the level-based open channel flow, where somebody's just put a metal plate underneath the sensor, and you get a completely flat line, and you're suddenly going, so what's going on here? I've had discussions recently where you've got the data within the instrument. So people are starting to talk about using the HART protocols that are already in the instrument, and using those also to help with the data quality. The decision I've had to have in the past is, I'm sat at a computer in the office, I've got a flow meter 60, 70 miles away, or 2 hours away in the car or whatever, and you're suddenly going there, so what's the problem here? But as we heard from Cathy, it's only the data quality is only going to become a massive problem, as well as everything else in the future. So it is really good. But we have got a question from Andrew Chappell of the agency. How do you set the initial percentile thresholds?
So you mean that those numbers in those kind of percentile definitions that I was putting on the slides? I think we've built those up through experience over quite a few projects working with flow data. I think we found those to work quite well as a kind of rule of thumb. I think it's probably something you want to keep under review and make sure you're looking at the reviewing from time to time the values that are being invalidated by the rules, checking that they're still appropriate.
I must admit, when I was at Anglian, we had a system which was upper and lower boundaries. So, and if a total daily volume was in or outside the upper lower boundary, then it would flag after 3 days, and that worked. It was rudimentary, but it worked. But certainly, it wouldn't necessarily cover some of the case studies that you had there. So where you,
I guess you had to set them up into.
Yeah,
you have to set them up individually for each site.
You did, yeah. We had a general rule of thumb, but as over the years that we found sites that were okay, then we could tighten those boundaries, tighten until we got to a break point, and that allowed the sensitivity to change, but not getting false alarms all the time. So, and that was the challenge. But to be honest, I don't envy the people that were in my situation at Anglian now, because they've got a lot more coming to hit their plate with EDMs, with UMON 4s, with final effluent, with UMON 3s. And it's going to be a case of bringing all that data together. That there's going to be a real challenge for the industry. So data quality moving forward is going to be, well, when we're talking, I mean, I said earlier, a rough figure of 500 million pieces of flow data every year. And that's 15-minute values. And that's if the data is pretty much perfect. What you'll find, what I found in the past, is you've got telemetry repeats. So it should be a neat every 15 minutes, but then you'll suddenly get a spurious data point from 11 minutes and 11 o'clock and 11:06 or 11:12, which was spurious, and getting those bits of data out, it can be quite a challenge, because sometimes you're going line by line by line through 100,000 pieces of data.
No, that's not good. I certainly at Ovarro we're thinking about ways that we can do more to help companies to automate these processes and provide tools that will help
it's
do
absolutely
that.
essential. And to be honest, I think we might have a bit of a change. We're going to probably switch Ronnie and Darren around, as I can see of the presentation that's queued up, because I think we're having a bit of technical challenges getting Sam into the feed at the minute. But yeah, I know Seeq are also going to cover that sort of packaging of data, and so thank you, George. Now, Seeq is a company I came across through LinkedIn, I think about 3 or 4 years ago, and spoke to them. They were over split between here and the States at the time, and I could see all of this data crunching that we're going to have in the following years coming up. I could see it starting to build 3 or 4 years ago. But at the time when I spoke to the person who set up Seeq, Michael Reeser, I said, you're probably about 3 or 4 years now. 3 or 4 years down the line, about six months to a year ago, I got asked about, Oliver, do you know any analytics solutions that we can have to handle all this data? And when I got asked the question about this flow forum, I immediately contacted Michael over in the States and said, do you fancy having a chat to everybody in the water companies? So at that, I'm going to let Ronnie and Darren take over, because I think they've got something really interesting to show us.
Excellent. Yeah, thanks very much, Oliver. Thanks for the introduction. And great to be speaking with you all. Good morning. Still morning. So excited to be speaking with you all on the subject of data and advanced analytics. So Ronnie Bains, I work within the Seeq organisation, responsible for our partnership region. So be a bit of a tag team between myself and Darren, Steele, during the session today. So I'll hand over to him a few slides. But I really wanted to start with an introduction to exactly what advanced analytics is and how we position that with the industry. So on that note, can you go to the next slide, please? Thanks. So there are many opportunities, with advanced analytics we see in industry. Data analytics, all these buzz terms we see in the industry really being used quite broadly now across industry verticals, but also within the water industry. Today, data itself can actually provide us with a lot of value, and it can do a lot of different things depending on how it's going to be used. And within Seeq, we position our platform to really be able to provide 3 pillars of support to our end user organisation. So the first is using that data correctly to enable SMEs, so subject matter experts, to get hold of the right information at the right time, independent of where they may be located. The platform Seeq, which we'll talk a little bit about later on, is really formed on the basis of no-code or low-code kind of development. So you don't need to be a data scientist to be able to really leverage the value the data we have can provide. We can easily cleanse and contextualize it, and it's really all about democratizing that data and getting access to everyone. So really enabling those insights to be provided to subject matter experts. The next point is the speed. So the way that we've architected Seeq and how it connects and uses data, both historical data and real-time data, is pretty unique. So it allows us to get those insights developed very quickly. So connecting into existing infrastructure, not providing an overhead to do that, and really integrating into the overall framework that our clients have. And thirdly, we really recognize that democratizing the data, getting access to everyone, is really when the value starts to be seen across industry. So once you have the insights and they've been developed and you develop correlations and patterns, it's then all about sharing that within your enterprise and collaborating with other members within your organisation, and really gaining that value which data can provide us to many of our customers on a day-to-day basis. Okay, next slide, please. Again, when we look at data, and I think probably some of the way that data is treated and discussed in the industry at the moment, it's point 4 that you see on the slide at the moment. The computation and the analysis of the data is really where a lot of the focus exists. So how do you gain insights from the data? How do you use that to develop patterns and correlations to help predict things in the future? Which is, of course, a very important point, but really there's a lot more. There's a much larger story to that. And if we step back to point 1, we position Seeq to be able to support the entire life cycle of kind of advanced analytics for the enterprise. So it all starts with getting access to the data, having the right way to connect into your data sources, time series data, being able to bring that in from multiple sources and amalgamate that and cleanse it. Then the next point is being able to contextualize it, so adding real context, real information to that data and how it can be applied. We then move into the ability to be able to search easily, make it intuitive to find your way around that data, index that data, and combine it with all the other sources you may have. And once this has been done, then it's a case of being able to compute and analyze and build correlations up, really extrapolate what that information is telling us, and be able to apply that in the future to really gain additional insights. An important component is also developing dashboards, getting the right visualizations in place so the insights you do develop can be shared and collaborated within the organization around whoever that needs to be. So again, the platform allows us to do that. And another important point is, we can start at quite a small point. So we can start at a particular unit level on a piece of equipment, and we can scale very quickly and apply that and grow that as the usage and the value really becomes recognized. So it's really all about the entire life cycle, ensuring that engineers have all the information, have the right system, being equipped with the right system, be able to provide them with the support across that entire kind of advanced analytics life cycle that you see on the screen now. Next slide, please. Great. So when we talk to our customers and we really see how data is being put in place to support their digital transformation strategies, they're really focusing on 3 areas. The first is enhancing the employee digital skills. So they do that by applying software that's been designed specifically for a task, and it really encourages the collaboration across their teams. This translates into much more improved productivity and results that really impact operations immediately. And in fact, when we talk to many of our customers, we see payback in weeks, not months or years. It's a really fast return on investment that we can prove and it's tangible. Secondly, after an initial wave of improvements in productivity, we see our customers really driving towards plant level optimization. So this involves predictive models to avoid costly shutdowns, improved asset utilization, and really increase the production of whatever their facility is doing. And of course, process optimization is put in place there to reduce costs. So it results in millions of dollars or whatever the currency is in the totality of annual savings. So these are the types of returns that we're seeing on a daily basis with our end users we work with. And finally, the most ambitious type of end users and customers we talk to, they really apply this at an enterprise-wide optimization. So they apply enterprise-wide and they set up benchmarking activities to really compare utilization, efficiency, cost avoidance, and lots of other KPIs across all of their sites to get a much better insight into how their overall business is performing. So you can do this, and you actually can improve how you allocate capital, where you invest in new equipment and products, the really way to focus on where the growth of the business needs to be. And similarly, again, resulting in a huge return on investment that is tangible and is quick, right? More importantly. Okay, next slide. So what you see on the screen at the moment is a high-level topology of the Seeq application suite. So we really have 3 applications within Seeq, the portfolio, and I'll briefly talk through that just to give an idea of how it's all kind of fits together. So starting at the bottom, we have different types of data. So it could be cloud data. We have very strong partnerships in place with AWS and Microsoft. It could be manufacturing data, so coming from any of those more kind of recognized manufacturing systems. SQL-based data, custom sources. We're very flexible in terms of what the data source is. If there is a data source available, it's very likely we'll be able to connect to it. Yeah. Okay. Sorry, a bit of an interruption there. Okay. I'll now hand you over to Darren, who will give us a deeper insight into, and also with application examples in the water industry, exactly how it's applied and some of the returns that the customers see.
Okay, thank you, Ronnie. Hopefully everyone can hear me okay. So my name is Darren Steele, and I have spent most of the last 23 years helping companies to transform their raw data and data sets to deliver decision support systems. More recently, I've been working with Seeq to equip engineers and subject matter experts with what I see as the right analytics software for the job. So as we saw in slide 3 from Ronnie, high quality data is really the foundation for any subsequent analysis. And in this section of the presentation, we'll take a look at different methods that can be applied to the data sets to address a variety of data quality issues. We will then take a look at some real world examples of how analysis can then be made on those cleansed data sets. So next slide, please. There's a small delay between while we wait for the slide there. So okay, so thank you. So if we look at the typical sources of data available for analysis in the diagram on the screen, you will see that we have the traditional sensor-based data coming from sensors up to the DCS or PLC or SCADA system. And we also have, with the advent of the Internet of Things, there's this new data source emerging where you've got sensor-based data that bypasses traditional control system hierarchies. And those smart sensors will wirelessly transmit values or timestamps to a data store that's traditionally cloud-based. And as we heard from the presentation from George Heywood, there are data quality issues with sensor-based data. There's a variety of issues that occur. Issues such as gaps in the data, signal noise, spikes and dropouts, sensor drift, and unexpected staleness in the data as well. However, in order to conduct a well-rounded piece of analysis, we should consider data beyond the sensor data alone. And data is now readily available from third-party providers such as weather service providers and satellite companies that provide observation data. And of course, those data sets are also prone to error as well. Then we have data from relational data sources such as maintenance information, the maintenance work order records from asset management systems like Maxima or SAP PM. And you've got quality data from lab information systems as well. And manual lab sample results also are prone to error, and also automated inline analyzers require periodic calibration. So with each of these different data sets, you have a potential for data quality issues. And let's not forget, energy pricing spot price information can also be a data source that you can plug in and merge with your operating data as well. And then we also have unstructured data now as well. So there used to be the situation where you'd have the operators would have a logbook and they would record data about the shift, information about the shift in a paper-based logbook. And now there's electronic logs as well where you can record information. That's valuable tacit information about the operation, which we should really, feed into and use to add further information to the flow data and other data sets. The application of that unstructured data and mining that tacit knowledge contained therein is probably worthy of a completely separate session. Now, for engineers that operate and maintain the plant and the network, there's a strong argument to for them to be equipped with an analytic system that can be used to cleanse data so that they can deliver maximum confidence in the results of any analysis that they will perform. Next slide, please. So let's take a look at some of the methods and options available to the engineers to clean up their data. So the first use case is around the topic of gaps in data. And this can happen for a variety of reasons, but it will have a significant impact on any calculations and any output from any analysis. So we really need to address this. And there's several options in Seeq that you can use to tackle this. In this example, you'll see there are some blue bars there, which are used, which are actually called capsules in Seeq. The capsules are user-defined periods of interest. And in this example, the capsules are used to identify where the gaps in the data occur. And then you have different options available to decide how you want to address those gaps. So in this example, the last known good value is propagated from the start of the gap to the end of the gap. So that's just one option. And that's a very quick, simple sort of no-code example. And there are other methods available. You can splice in an average value if you wish. You can interpolate between the start and the end point of the gap, or you can apply a step function. So there's different no-code and low-code methods available to address those gaps. And those capsules can be used in many ways. For example, if you need to make a multivariate model, we have multiple inputs to generate an output. You really need to exclude bad data. And those capsules can be used to identify periods of bad data or bad quality data and make sure that that isn't fed into those multivariate models. So the capsules can be used in many ways, and also they can be used to provide alerts or flow warnings or operating envelope limit exceptions as well. Next slide, please. So that's addressing gaps in the data. And the next slide will show how we can address things like dropouts and spikes as well. So the engineer or SME, they can see that or apply rules to treat dropouts and spikes. And again, there's several methods available in Seeq to do this. So you can create soft sensors where the dropouts have been replaced with derived data values. That's one option. And then that soft sensor can then be used as a more reliable input into the data model or piece of analysis. Likewise, with signal noise, a soft sensor can be made that filters out the signal, the noise around the signal. And there are several filters available in Seeq to do this. So it may be you want to apply a low pass and a high pass filter first to remove those spikes and outliers. And then you can apply an agile filter to remove noise around the signal. So a real world example would be where you're looking to create an alert on a frozen or broken valve. And the noise of the signal may hide the true state of the valve. So it may look like there's movement when actually there isn't any. And you're expecting valve movement. So it's important to highlight here that, domain knowledge is often key, really key to selecting the correct filtering method. I'm just picking up some keyboard typing in the background, so I don't know if somebody needs to go on mute there. Thank you. The tacit knowledge and that domain knowledge is really key to applying the correct filtering method here. I think in a ideal world, you could sort of set one algorithm and it would take care of itself. But actually applying the wrong type of filter could actually filter out good data as well. So we have to be aware of that. For example, the Savitsky-Golay method, that's a smoothing filter. That's typically used to smooth out a noisy signal where the frequency span without noise is large. And there are also, it's also called a digital smoothing polynomial filter or least squared smoothing filter. And this filter performs better in some applications than standard averaging filters, because those filters tend to filter out high frequency content along with the noise. That's an example where a little bit of tacit knowledge about what it is you're trying to filter comes in handy. Savitsky-Golay filters in particular are more effective at preserving high frequency signal components, but less successful when it comes to rejecting noise. Let's be careful here when we're deciding what filters to use on which kind of data. Next slide, please. So, in addition to cleansing signals, it should be noted that data streams can contain good quality data, but it could be for periods of bad operation. The data from the periods of bad operation should not be trained into models when attempting to estimate and forecast expected good behavior. I am getting some more noise in the background. I wonder if don't know if anyone else can hear that, but probably just needs some more people to go on mute there. Yes, I still hear that background noise. Okay, right. Okay, we'll carry on. Okay, so the data from periods of bad operation, you don't want to train those into your models. Especially when you're attempting to estimate and forecast what you think is expected good behavior. If you don't exclude that good data from bad periods of operation, if you don't exclude that, then you'll end up comparing actual versus bad instead of comparing actual versus best. And you'll also be training anomalies into your model. For example, you need to filter out data from periods of unplanned and planned outages. You need to filter out data from periods of unstable operation, and you need to exclude data where you have periods of significant disturbance. You also need different models for different modes of operation as well. So if someone tells you that one asset model fits all, I would be tempted to question that. And again, that's where the tacit knowledge comes in. You really need the engineers and their intimate knowledge of the plant, the engineers and operators with the intimate knowledge of the plant and the network. And that's required to help identify those periods of good operation and then use those, that data to train your models. And Seeq really facilitates this process. And capsules, once again, play an important part where conditional logic is applied to indicate those periods where data should be included or excluded. Next slide, please. Okay. So once your data is cleansed and prepared, you're ready to start analyzing your data. And there are a variety of ways to analyze data sets, ranging from traditional descriptive analytics to situational awareness-based analysis. We've also got optimizations, forecasting, and predictions, univariate, multivariate predictions. What I also see as well is two distinct types of analysis. You've got that routine analysis, where you build it once and then you want to apply that across your filters or across pumps or across assets, and it's going to be routine analysis. You've also got that ad hoc discovery analysis, and Seeq supports both of those scenarios. Next slide, please. And I think we'll skip on to the next one as well, because we'll look at some real world use cases of how companies have, yes, thank you. So here we have some typical use cases across water treatment and wastewater treatment. And we can see a variety of use cases ranging from energy reduction to predictive maintenance on equipment and event detection, and sort of flow assurance as well. And perhaps one aspect that we should highlight here is the use of Seeq to provide virtual sensors and inferences. The water networks are vast, and it's cost prohibitive to instrument the entire network. And instrumentation can also be limited to one or two simple discrete signals on some equipment as well. But Seeq enables engineers to create virtual sort of inferred sensors. That's a more cost-effective means of enhancing decision support. But what we find that anomaly detection doesn't necessarily require fancy multivariate predictions and machine learning. Next slide, please. So in the next example, we'll see how one utility company used their cleansed data sets to help make some improvements. This is Tas Water from Australia, and they recently presented how they worked with a consulting company and Seeq to monitor their pump stations for deviations away from normal profile. Tas Water informed us that sewer blockages were a real issue for them and that they really needed earlier warning of potential blockages to help coordinate more timely remedial action. But this was a challenge since not all pump stations were heavily instrumented. However, with Seeq, they were able to create inferences derived from the pump run cycle times, and then they could create reference profiles. And the earlier warning anomalies were then derived from being able to see persistent and significant deviations outside of those normal profiles. And then they developed a standard usage profile for each pump power station using those reference profiles. Then they could take that single model and use it as a template and then deploy that across other pump stations as well. And now they monitor all pump stations for those large deviations from normal. And it's also integrated with their PI system as well, so they get early warning notifications, and they can send those alerts to the operations center. Next slide, please. So in the next example, this is water treatment sand filters, and this is where they have signals that were susceptible to dropouts, and trying to cleanse all of this data in an office-based spreadsheet and replace those signals, those dropout signals, was really tedious, cumbersome, and it wasted precious time. And not to mention, the challenge of trying to apply that method across all sand filters. A spreadsheet just wasn't viable. And they had a traditional approach of set it and forget it. So they would perform filter washes on a scheduled basis, whether it was needed or not. And the spreadsheets they were using, they were not maintained or updated. So the run lengths were not adjusted, which also led sometimes to solids clogging up in the filter, which meant they had to shut down and replace. And that was time consuming and expensive. So to challenge business as usual, they utilized Seeq, and the engineers were able to create a seasonal predictive model and maximize those run lengths whilst ensuring that filter washes were performed when necessary. This meant that expensive shutdowns were eliminated and another volatile office spreadsheet was deprecated. By using Seeq to create soft sensors for monitoring metrics such as unit filter run volume, quantifying costs of each backwash, the engineers could visualize each backwash cycle overlaid on subsequent cycles and also compare to other filters. And then they could check for emerging mechanical issues as well. So in the filter monitoring report, you'll then see that capsules appear again as green bars for each cycle, and there are red capsules for the actual backwash events as well. Those capsules appear once again. Next slide, please. So in summary, we've looked at a variety of typical data sources and discussed the need for cleansing data. We also looked at examples of data cleansing operations and the subsequent use of the data for end-user driven analytics. And rather than Seeq being at the heart of the solution, experience really tells me that it's the subject matter expert, the engineers, using their tacit knowledge and the Seeq functions to solve business problems. That's really at the heart of the solution here. And this is a user-driven approach that is really gaining traction across many industries, not just the water industry. So next slide, please. So to end, thank you very much to Ronnie, and thank you very much to the WWEM team for giving us the chance to present today. Be delighted to answer any questions, and also please feel free to contact Ronnie or myself if you'd like to discuss the topics further. So thank you very much.
Thank you, Ronnie, and thank you, Darren. I must admit, I saw Seeq 4 or 5 years ago and went, wow, there's something that we need in the water industry. And I think it's even more and more important now with this mountain of data we've got. To me, certainly the capsules, getting that feed in from the FFT monitor, that feed in from the EDM, and of course all the data quality work has that huge potential for us to overcome. And that's just one application in the water industry. Yes, we're all wastewater flow people on this forum at the minute, but the potential to take that window capsuled approach and bring in the streams, and then, as we saw from Cathy earlier, bringing in rainfall data, potentially bringing in radar data, is such a powerful technique. And we'll see tomorrow actually at the pollution forum somewhere where the hyperlocal forecasting is being used, and I don't think it's used enough. And actually through the Seeq analytics packages here we see here, there's an incredible power that we can take that step on digital transformation from step 1, step 2 that we are now probably up to steps 4 and 5. I was on a call yesterday with the control room forums, and they were just talking, how do we take that step? And I think they were accepting it's probably going to take 10 years. And in some cases, you can say, well, that power, those tools are here now. So is there any questions from the audience at all? So thank you very much, Ronnie. Thank you very much, Darren. I'm hoping now I've got Sam Green.
Hopefully you can hear me, if nothing else, Oliver.
I can certainly hear you, Sam, which is great. There's been some work in the background to get Sam on, which switch the sessions round. So thank you, Sam. I can see you now. It's even better. Great. Sam is going to talk about things from a data quality and wastewater flow compliance perspective. So I'll let you take over, Sam.
Thank you very much, mate. Good afternoon, everyone. As Oliver just said, I'm Sam Green. I'm one of a few analytics managers at Southern Water, and I've been looking at flow compliance on and off since 2013. And what I'm going to talk about today is actually, from listening to others, going to build on what Cathy said, what George has said, and then what Darren and the other guy, sorry, I've got your name, has been saying this morning. Ronnie, thank you. Sorry about that. So a little bit about me. As I say, I've worked for Southern Water. I basically am trying to do more advanced analytics inside of the company. We cover every aspect of the company, so we're not flow focused, but we have been doing work on this for a long time. So I'm going to show some examples of what we've done, and I hope tell a bit of a story, I hope. So next slide, please. So why do we talk about flow? What's the challenge? At the moment, flow compliance is quite poorly understood in the industry. We've got quite a few inconsistent approaches of how we can do it. We've got lots of people running on spreadsheets, some far more advanced than others. We have a lot of historical focus that's been elsewhere, which has caused this problem, most of which has been on end of pipe compliance. I've put in a couple of acronyms here, DRQP, data rich, quality poor, and GIGO, garbage in, garbage out. We definitely have this problem with flow data, with data in general, frankly, but we have this problem with data where we've got a lot of it, but we're not doing much with it because we don't understand the quality. We don't understand what's really going on with it. And we're making poor decisions because we're feeding it with very poor quality information. On top of that, there's a very real operational need to understand what is going on. We need to understand our sites, we need to understand their compliance, and we need to be looking at fixing issues. And again, this is what we've been doing at Southern since 2013, trying to find sites that need to be fixed and then trying to fix them. And all of this comes down to the last point here of compliance and environmental impact. The picture there is actually of the River Ouse, which is right near where I live, because everything we do on flow compliance impacts our environment, our local area, and if we pollute those areas, well, it's not very good, is it? So it all comes back to us. Next slide, please. So what I'm going to talk about are some data quality pillars. Now, there are lots of models of data quality pillars. I've seen some ranging from 4, and I'd swear I saw one with 13, but I've picked one that has 6 pillars. And those 6 pillars are accuracy, completeness, consistency, timeliness, uniqueness, and validity. Hopefully people know what some of these are, but very briefly. Accuracy, how accurate are the results we're getting? Complete, are we actually getting everything we expect to be getting? Consistency, are we always getting values that are within the range we expect? Are they meeting the sort of values we expect to fit in the database? Timeliness, are we getting them quickly enough or not? Uniqueness, do we have repetition? Do we have issues there? And validity, yeah, sorry, my brain just went there. Second time I've done this, so excuse me. But for the speech today, what I want to talk about are 3 key areas. And those are accuracy, completeness, and timeliness, as you can see highlighted here. So next slide, please. So completeness. This one's really easy, thankfully. We know from analog monitors that we are expecting a certain amount of values per day, per week, per year. So these expected ranges, if you're using 15-minute data, we're obviously expecting 96 a day, 35,000 per year. If we go to 2-minute data, 720 per day, 262,000 per year. Trying to look at completeness, am I getting as much data back as I need, is thankfully quite easy here because we know what we're comparing against. But when we go to the next slide, please, you'll see digital monitors. Now, this is quite hard to do because we don't know if we're expecting this thing to go off or not. We don't have a certain number of expected values per year. So we don't know if this thing's broken. We've got no events. We don't really know what's going on. So this can be quite hard to assess. Next slide, please. So what can we do? Analog-wise, as I say, is actually quite easy. It's very simple to set up, and I'll show you an example of this later on, an automated review of the number of data points that are being returned. You can see quite quickly how many you've got. You can find the gaps very easily. And then you can say to someone, did you know that flow monitor A, B, C, D, E, whatever, that is not returning data as we'd expect? Can you go have a look for me, find out what's wrong with it, and fix it? But for digital monitors, as I said before, it can be quite challenging. So to do this, what we need to start understanding is the site. And this goes from what Ronnie and Darren were saying earlier around actually using SME knowledge. So it's actually trying to understand the site. Do we have regular comms issues? Do we have seasonal patterns of expected behavior? Do we expect the site to actually go to storm or not generally? Have we had long periods where this thing is not activated? And it's actually trying to think about these issues that we could experience, that we can then start designing and building analytical applications or programs that can then review and feedback to people whether we think there's an issue or not. So next slide, please. Thank you. So here is just a very, very quick example of something we do currently at Southern. This is actually used for a couple of purposes, the chart here. It's a frequency distribution histogram. And essentially what we're looking at here is whether the flow control on the site is working or not, and whether we expect the site to be going to storm or not. So what we're using here for completeness is actually for a digital monitor, because we look at the first top site and we say that's got a PFR to dry the flow ratio of 3, or PFF as it's also known, a pass forward rate. So we expect this site to go to storm quite normally. I expect to see activations on my digital monitor. I expect to see a clear flow control peak in my frequency distribution histogram, which is actually what I've got on the top example. A bit hard to see because it's a bit zoomed out, but it is there. The second chart has actually got a PFR to dry the flow ratio of over 6. So for sites like this, where we basically have over-designed back in the day, we do not expect these digital signals to go off. We don't expect to see a flow control peak. We don't expect to see certain issues. So what I'm trying to explain here is, by understanding the site, understanding what we've got going on and understanding how it was designed all those years ago, we can start looking at our data and saying, do we think there is an issue here with my digital monitor? Do I think there's an issue of it not going off when I expect it to? And one of the things I've actually stolen a quote off here from the EDM Good Practice Guide is it's saying that where we have no events recorded, so we've got a completeness gap in our digital monitors, we should go and have a look. And this is kind of what we're trying to say here on this slide. If you've got a site that you expect to be going off, you can very easily work out if you expect to be going off or not. If it's not going off and hasn't done for a period, send someone out, get someone to have a look and try and work out if you've got a comms issue, monitor issue, or what. Next slide, please. So, accuracy. So, analog again, this can be relatively easy. I've put relatively for a good reason. But with an analog monitor and a flow monitor, what we're expecting is within a certain band. You don't expect negative flows. You don't expect flows to be exceeding your pass-forward rate or your pass-forward flow, depending where it's located, of course. And you know the sort of ranges you're expecting based on your connected population and storm estimations. You can know very, very quickly what you expect this thing to be telling you. You also can very easily work out seasonality. You can take the time series, decompose it down, and say, we think we've got flow spikes each winter, as we generally have, and we can actually show this sort of thing. The only challenge is we have a lot of uncontrollable outside variables. And this is where we come back to the weather point that's been mentioned a few times already. You get large storms, very large storms, or very sudden storms, and you can get some very odd flow patterns. But overall, it's quite easy at a very high level to say, is this flow monitor in the range I expect it to? And is it in that range for the right time of year? Next slide, please. Digital monitors, it's still fairly hard. There is an expected pattern to activation. You have a high flow, I expect my digital monitor to go off. Simple. That is something we can definitely build, and we have built. So you say, I've got a flow that's hit PFR, I've not got a digital activation. That's a bit strange. We should go and send someone out to have a look at this. The challenge we get here is there's a lot of potential for interference. And I know Cathy mentioned this on her talk earlier, where she was saying about plant life or wildlife even getting in the way of an EDM monitor and sending it off incorrectly. And it'd be quite hard to work out sometimes if your digital monitor is the one that's broken or your analog monitor is the one that's playing up. It can be quite hard to manage, to work that out. But there's still some things you can do. Next slide, please. So, for this, what can we do is more around understanding your seasonality, trying to build automatic anomaly detections, and I will go on to some things for that in a second. And if you have other flow meters, there are very easy things you can do on site to compare them against each other to say, actually, is this thing operating in the same sort of range as another thing, another flow meter? And we can say, what sort of variance have we got between them? On the digital side, what you can do as well is compare your digital activation to other site assets. Do I have, for instance, say a storm tank level monitor that should be going up when my EDM monitor for the storm tank is saying there's flow going in? If the answer is no, something's gone a bit wrong there. Have I got pumps that aren't running? I've got flow that's backing up, yet I've got no EDM activation. If the answer is yes, there again is something wrong there. There is business logic you can build into analysis to actually look at this. And then the last point here is obviously just checking your site frequently and doing regular maintenance, because obviously if you're not maintaining or calibrating your instruments, you're going to have some problems. But next slide, please. It's just a very busy slide, and I'm sorry for that. But essentially, these are some examples of things we are either doing today or that we're planning to do in the very near future. So I'm going to start in the bottom left, as it is on my screen. That chart in the bottom left with some dots above it. This is a very simple compliance check that we run. This is made up data, by the way. That basically says I've got a flow trend going off. I've got some spill activations going off. Are they happening at or within my expected PFR range? What's going on? But what we can also see is towards the end of the time series, we've got a spike going up. It's hitting the PFR range, but we do not have the corresponding digital activation that we expect. This is something that we do actively pick up. We stick it in a big list and we send it to people saying, did you know that sites A, B, C, D are having this problem? The next one across going clockwise, this is a bit of a messy screenshot, but this is from PyAF because we also use the Pi system. This is an automatic detector for flatlining and for things going outside of set ranges. And again, we're talking about below zero, that sort of thing. We set this up a long time ago, and it's still run to this day, because we can just have this run 24/7 on a server, always checking for errors that we think are going on, that when we can notify people via email, because it's got an automatic email system to say, did you know that this site has had a flat line and it's lasted a day, it's lasted 2 days? You might want to go and have a look at that, because obviously we start falling into technical failure territory if we don't fix these things. And yeah, so that exists. It's a very easy, very quick way of doing things. Just look for values that repeat themselves, tell someone it's happening. On the red and green chart, I'm going to say, on the right, this is a cross-correlation function. So Southern Water installed a lot of monitoring the AMP before last. So we are quite lucky in having a lot of available monitors. What we have done here is we've compared an M-certed monitor at the back end and compared it to a non-M-certed monitor at the front end. What we are doing, and again, this is made up data, but what we are doing is we're comparing the two trends against each other, and we're running them across a cross-correlation function. The idea is that that cross-correlation function will apply an automatic lag, and we'll try and align these two things together, and then we can compare the means. Sorry, there is someone talking. Thank you, whoever muted them. But we can then compare the two means together. The idea is we can then detect drift. We can detect monitors that are inaccurate against each other based on a known validated monitor. So we can say, here's my back-end monitor. It's M-certed. I know it's accurate. Here's my front-end monitor. It's not, but it's actually incredibly close. I know by comparing the means and doing this CCF that this monitor is within the same range, or indeed, as the second chart I've made up, it isn't. So we can start saying to people, did you know this is an inaccurate inlet monitor, this is an inaccurate outlet monitor? We can start actually telling people problems just by comparing the two together. A very simple test, but quite an effective one. And the third thing here is kind of in the middle, and this is something we're exploring at the moment. This is actually taken from a paper. The name of it's actually in that little box. But this is using a sliding window machine learning algorithm. And what that's doing is it's taking a known seasonal trend on water levels in this actual example from the paper, and it's saying we expect it to be within this sort of range. And it's then saying with a confidence level, is your flow reading within that expected range? The idea is, obviously, we can then use this for 15-minute or 2-minute or 1-minute data. We can dump it through and say, this is my expected pattern, and then try and find those that are falling outside of the confidence interval automatically. So we're still building this, and we're not sure if it's going to work yet. But this paper is based on water level monitoring. It was actually done in China, if memory serves. But we found this paper when we were looking for the new MCERS guidelines, and or the new compliance guidelines, I should say. And we think this sort of technique will allow us to do on scale, very quick, live monitoring of a time series trend with seasonality, and telling us where we have data points that fall outside of what we expect. And again, this is where we start flagging the data points as good, we flag them as bad, or we flag them as ugly or suspect. So we have a lot of work going on here. And again, what we try to do with this is feed it back to the business to let them investigate. There's no point us running this and just sitting on it. What we do every single month is we take all of this, summarize it together in some form or other, and we send it out. Obviously, I say some for other, there's reports, but we send them out regularly to say, did you know these sites have problems? Next slide, please. Timeliness. Okay, I've kind of, excuse the language, bastardized this a little bit. Usually timeliness is making sure people have the data they need when they need it. What I'm trying to say here instead is we need to be considering granularity of data. We need to be considering how small a time period we need to be using to compare to EDM events. So analog monitors, they return data currently, today, every 2 or 15 minutes at Southern at least. And they're giving us a whole range of things. They're giving us averages, instantaneous values, accumulations, and totals. So they're giving us quite a lot of data. But if we move on to the next slide, please. Digital monitors, we have these every second to the second. So every time they go off, it's a very defined set window to the second of what's going on, and that is either on or off. So we have very rich data sets here. But if you go to the next slide, it's quite hard to compare them against each other, because then we're saying I've got a 15-minute flow monitor that's working on averages, which is the best one to use. So we got 15-minute trend, there's my average, 15-minute trend, there's my average. And then over that, we have a EDM window that says over these averages, you have had a spill event. And obviously, these things do not always line up. Indeed, we don't expect them to line up. So what I'm trying to say here in the timeless one is we need to focus on granularity. And I believe personally, and it's a bit of a contentious one, I believe we should be exceeding the requirements that we're getting from the agency. When they're saying go to 2 minute, we should be saying, well, actually, I should be looking at 1 minute, because I'm going to get 2 minute EDM reportable windows, and I'm going to have a 2 minute flow, and I'm going to have the same problem. I'm going to have a smaller window to compare against the smaller average being returned. But the more granular data we get, the more confident we can be in saying if we were compliant or not. And if you go to the next slide, please. This little slide here is just trying to very badly show this. So again, completely made up. But you've got an EDM window there. And we started at the 15-minute window where you had very few points. You go to a 2-minute window where you have a lot more, and you go to a 1-minute window where you have absolute tons. And when you compare what we're being asked to do with new guidelines, where it says ignore the first flow or ignore the first 30 minutes of flow, and you think, well, actually, I'm comparing this against a 2-minute window or a 15-minute window, that's going to be really weird to do. It's not going to quite work. So what I believe we need to do is try and exceed these requirements a little bit, and to say, actually, if we have a slightly faster return of our flow data, we could ignore the first point, we could ignore the last point, because we probably should do that too, and we can actually start understanding what sort of flow we actually had during an event. Last slide, please. Or next slide, please, is the last one. So in conclusion, in my opinion, we should be using our data quality pillars and saying, these are the problems we could face. These are the things we should be addressing. By understanding that, we can then build and develop analytics, automatic as far as we can, to try and address and account for all the problems we've got. We need to get business buy-in, because we need to be driving fixes to these problems. There is just no point sitting on something saying this is broken and it's been broken for 6 years. And we need to aim to exceed. And last slide is just questions. Thank you.
So thank you, Sam. 1 minute frequency. Can we actually cope with it?
I think we can. As long as our outstations can cope with it, yes. We have a problem with some of our older kit, obviously, where it might struggle to hold so much information. I personally believe, yes, we can. Modern storage of data is incredibly cheap to store vast amounts of information. And there are a lot of programs, like the one we were talking about earlier, that can actually process reams of information insanely quickly, doing in-memory processing or the like. So I do believe we can do it, as long as we aim for automation. If we're talking manual, no.
No, I was going to say, because mostly what we're dealing with now is manual.
Yes.
I would agree with solutions like we've just seen from Seeq. And to be honest, I saw the potential in that a few years ago. That sort of thing, I think we can, yes, put in that data. The outstations won't cope with it, but then again, as we move away from PSTN, maybe there's that opportunity. I mean, for those not aware, the PSTN, which is the old copper phone lines, the private lines on wastewater treatment works are going. Is that an opportunity to then shift over to something that will handle that? I don't know. I don't know the cost of that. And maybe it is, maybe it isn't. I know when I looked at this with a water company, the telemetry bill was gonna absolutely skyrocket, going to 2-minute data. So if you're then talking 1 minute, I also know Thames Water of course, done the really adventurous thing of universal smart metering, which they're delivering now. One of their problems was data handling the data coming in. Now that they've gone down that route, I've seen their water efficiency manager, who absolutely loves smart meters. The insight he's got from the data is incredible. I mean, absolutely incredible. I'd love to go to 1 minute data, but oh my God, it worries me. So we've got a compliment from Cathy. Sam, absolutely brilliant presentation. Really reassuring to see Southern's approach to data quality aligns with Thames Water's. You covered briefly how we need to identify sites where we are expecting spills but hasn't shown, indicating a monitor error. Have you found any useful automated process for this, or is it a manual process at the moment?
Everything we're doing today is automated. So we have written a lot of scripts. So we are code heavy, unlike some of the software you can get off the shelf. We are very code heavy. We have written a lot of scripts in our coding language that process all the data for us with an API, giving us easier access to our telemetry data. Essentially, what we've done is we've used our data science team and some of the analysts who work for me to basically build us a lot. And they have built us a lot based on logic we've had back from the business and a lot of learning we've had. As everyone knows, Southern Water's been in the news a lot. We've learned a lot from what's happened. We've taken a lot of these learnings and we've shoved them into code. So everything is automated. We can detect times where we've hit PFR and there's no activations. We can detect times where our storm tank levels aren't going up when we've got an EDM saying there's flows going in. All of this has been automated. We've used R. There are many other options available because ours is insanely code heavy.
So for an organisation who hasn't got you, is it possible?
Yes, and well, yes, there are commercial off-the-shelf products. I mean, we had one shown to us earlier that can do this sort of thing. I also believe that most companies do have a data team. I found this numerous times working with numerous organisations. Everyone thinks they can do data. Everyone does. And then everyone does it in Excel, or people do it wrong, or they don't understand the principles of what they're doing, and they just end up doing something that could be good. Now, there's good stuff out there, but everyone just kind of thinks they can do data. But companies have data teams for a reason. You have CDOs, chief data officers, for a reason. You have heads of data for a reason. Data is a new industry. Most companies will have a data team. I'd say use their expertise. Give them your SME knowledge. Give them challenges you've got. Tell them what you're trying to achieve. And shove it at them.
As simple as that. Yeah,
it's taken us years.
Yeah, I know, and I'm being facetious there, but it's to me, yeah, I can do things very, From Cathy, thanks, Sam. Really shows how important data science is to help advance our understanding here. I can do a lot of that. I can look at the data. I can what George presented earlier, and what Ronnie and presented. I can do that manually. I'm one of the subject matter experts. I can look at flow data and go, yeah, there's your problem right there. But converting my brain into automation via a data science team isn't necessarily easy.
No, it's not. Sorry to keep waffling on, but no, it's not easy. There's a framework that I rely on and push to my team all the time. It's called CRISP-DM. It's very standard. It's the cross-industry standard process for data mining. But there are two really key parts there, and it's understand your data and understand what the business is doing with your data or how it's using it. You can't be a good analyst without doing that, and you need an SME knowledge to help. It's not quick, especially on something that requires a lot of knowledge like this. But it's not impossible.
It's interesting because I think really data management wasn't part of Flow or hasn't been part of Flow. I think now if we bring if we bring FFT, DWF, spills to the environment, EDM in there, I think really, and I think this is why this particular session this morning was asked for quite strongly by the water companies, was I think data management is now becoming absolutely essential in Flow. And it shows what you're doing and what tools there are out there. And you've obviously developed it for Southern. I think Cathy's doing it in Thames. I think there are companies out there who absolutely need the data skills and don't necessarily have them, which is interesting. So what do you feel with? I mean, I can bring pollution in here really because flow management and pollution almost go hand in hand. We're talking about pollution tomorrow, and the amount of quality data coming up is huge. Where do you see the main pain points? And George, feel free, Ronnie, Dan, feel free to come in here.
I was going to say, was that to me? But no, our pollution analysis is very challenging. Well, we often find it's understanding the root cause. Yeah, the root cause understanding is honestly important. We need to understand what's causing an issue. If we don't have a clear root cause analysis, it's very hard to then predict if it's going to happen again. Try and find other sites that could have the same problem, and it's just hard to understand what's going on. So to me, the actual clear understanding of faults is key, and that's something that companies do struggle with because often it's free text. Well, I've seen it in free text a lot, but yeah, that's the challenge in my view.
I was going to say, one of the things I picked up from Ronnie and Daniel saying it was that unstructured data. There's a lot of it around there. I suppose that brings in the situational awareness that we're having. I don't think we've got the situational awareness, or not as much as we've got, and we're bringing in these flow monitors that, with a bit of everything, meld it all together, meld that structured unstructured together, and we've suddenly got a situation we understand much better.
Yes. Hi. Yes, Oliver. Yes. I agree. I think there's situations where you're mining the data to detect those anomalies, and then you're sending out engineers to investigate the anomalies, and then it's important to capture the information about that anomaly. So, was it a real anomaly? Or if there was somebody who put a plate under the sensor, is that information recorded? And if it is, you can then use that, because then that profile, that anomaly profile, means this is the type of issue that you can expect. And then you can monitor to see, well, monitor the data, if that profile reoccurs. And if it does, then you've got a potential apparent cause diagnostic, where you can say, okay, we've seen this error pattern before. The last time we saw it was at this site, and and this was the issue. And this is what we recommend to resolve that issue. And this is how long it will take as well to resolve that issue. So you've got all that other sort of follow-on information. I think often anomaly detection kind of throws it over detects the anomaly, then you throw it over the fence, right? Whereas I think, as this evolves, we can add more information around that anomaly to help troubleshoot it and take remedial action.
So it's interesting because we're getting now, there's this wonderful protocol that was only invented 30 years ago, and a lot of people are talking about the HART protocol. Now we've got it in a lot of the instrumentation, but again, that can help. What you're talking about is almost a multivariate approach at the data level, the sensor and data level. That's, I think, possibly where we can bring in that intelligence, that anomaly detection is from the HART protocol, almost on a separate feed. Now, actually, to be honest, the Seeq platform's ideally set up for that.
Yes, platforms like Seeq, I think, can reduce the burden of code as well. There's some great data science algorithms that you want to tap into and leverage. There's a lot of operations where you perhaps you can't use a spreadsheet to do it. You can't use a business intelligence tool to do it, and your engineers, or you may not have the data science capability to code from scratch. And you don't always want to code everything from scratch as well. I think applications like Seeq, where it's easy to use, easy to learn, you can actually automate a lot of the data wrangling and take out a lot of the heavy lifting. And then you can plug in, those advanced algorithms from using R or Python, and plug those in into Seeq as well, so that then Seeq allows you to use those algorithms and the data feeds together in one environment, and that might actually be a very cost-effective lean solution.
Yeah, we've also got a nice, interesting sub chat going on in the chat window as well here, and it's all about, yes, the need for the subject matter expert intelligence, and also adapting probably at a site level. George, I know you've got a lot of experience in that, in looking at the plant level. What are your thoughts on the challenges coming up?
I think that one of the problems here is that we're making a bit of a cottage industry for processing all this data, for manipulating the tools that are needed to analyze it, to validate it, and so on, to review the anomalies that are detected and alerted and so on. I think that the problem here is that we're going to make a lot of work for people to do, and there won't be the people to do it. And I think we need to find ways of increasing automation and making sure that the automation that we're putting in now isn't actually just generating more alerts that more people have to deal with.
Yeah, I mean, agreed. It's certainly that skill does worry me, and there's obviously a shortage in data science. There's obviously a shortage in the process engineering, but I look at it, and I've quite frequently look at the sums, and when we start shifting to 2-minute data, I start suddenly thinking, well, that's going to be billions upon billions of pieces of data. And you're right, George, it is going to turn into a cottage industry to a certain extent. But in some ways, I'm finding it difficult to avoid that. But I also honestly think with WWEM that we're putting in now, we can use that data for treatment works. So we're going to see artificial intelligence solutions tomorrow. And that particular supplier, I've turned around to them and said, well, actually in the future, you're going to get the flow to full treatment monitor, the flow into the works monitor there. How can we use that? And yes, we're doing this on a regulatory basis now, but as we saw from Cathy, there's incredible value from the data. How can we create, and I suppose this is the challenge, how can we create a system where we can manage, we're managing quality through the network pretty well nowadays. How can we create that we're managing flow too? And I think it's going to be very hard to avoid the cottage industry, and I think you're right, George. But have we gone too far down the path? Maybe. Don't know.
Yeah, I think the other thing is that we're all working on the same problems and solving them individually in different companies, and we need to do more to create collaboration across the industry.
Agreed.
to so that that work is being shared. I know that can be tricky, but I think that's what we need.
I certainly think Ofwat would not forgive me if I didn't mention the Ofwat Innovation Fund, and that's probably a route for collaboration. Anyway, I'm not 100% sure if we're live now because I can't see us on the screen, so we have overrun. If we are live and people can still hear me, we've got our third session of the day, which is very much an update on flow technology, with Alistair MacKinnon from Pulsar talking about sewer network monitoring, and an interesting sensor that I've been seeing developed over the past, well, I've seen it for the past 6 months now, and I know it's been 3 years. So do have a bit of lunch now, and thank you to all of our speakers for this session. I think it's been a really productive session. Thank you, Andrew, for saying you can still hear. So do join us at 1:30, where we will have a bit of an update on the flow technology that's available to the industry. Welcome back to this final session of the Virtual Flow Forum. In this session, we're going to be very much talking about giving an update on the flow technology. We've got some really interesting technology. We've got Alistair MacKinnon from Pulsar talking about low power sewer network monitoring. We've got something new onto the MCerts market, or potentially onto the MCerts market, and I think they're looking for places to trial if you want to get in touch with them. We've got Alex Keys from Augvald about measuring by microwave. Some of you may remember the microwave flow meters that we were talking about 3 years ago. This is next generation on, and we'll see some really interesting stuff there. And to finish us all off for the day, we've got Matt Westgate and Pete Devine from Vega. And I know you're all very familiar with Matt. So at that, we'll start. I'll hand over to Alistair MacKinnon of Pulsar. So Alistair can talk to you about low power sewer network monitoring.
Thanks, Oliver, and thanks everybody. Just a quick introduction to myself, Alistair MacKinnon. I'm the Global Director of Sales for Pulsar Measurement. Been in the industry for, 30 years now, and 23 years with Pulsar, and I've seen a lot of developments with instruments over that time. I want to talk to you about low power sensors. If everybody was on the call this morning about the data, it was really interesting and harvesting that data, but you've really got to get decent data out of the sensors. And I'm going to talk about that, as well as the ability to create a low power environment to be connected up to loggers and these type of things. So we supply a lot of EDM M-certed devices and have been doing that for many years now, and have recently had a unit M-certed for EDM, and we've worked with a lot of the water companies and installed quite a number of them over the past year, which has been very interesting. But I'm going to go a little bit off piste, because I'm going to talk about other sensors and low power sensors from there. So can I have the next slide, please? So quick agenda. Where are they used? We'll talk a little bit about that. The development of the contactless low power sensor, just a slide on that. We'll talk about the DBI and the microflow eye, our intelligent solutions for sewer network monitoring, and we'll bring in a few case studies and applications at the end with regard to river monitoring, irrigation, spill monitoring, but really concentrate on the sewer network monitoring, and tell you a little bit why velocity and level are two variables that are pretty critical in that kind of monitoring arena. Next slide, please. So where are they used? Low power sensors can be used in various different applications. As you can see there, I'm one for very much pictures rather than bullet points. I think they speak 1,000 words. So you'll see there a microflow eye, intelligent velocity sensor, and a DBI level, intelligent level sensor in a sewer, on a CSO discharge, on a tank farm out in Texas, and monitoring chemicals, connected up to a node, a remote telemetry node. You can probably just see that off the top of the tank. On irrigation channels and hanging off bridges, monitoring rivers in flood conditions, or monitoring flood conditions. So you can find sensors and low power sensors in various different aspects and applications. Next slide, please. And what do we need from a low power sensor? Well, we certainly we like to promote non-contacting. We do have contacting devices in the range, and you can see in that picture, I told you I'm going to show you lots of pictures today. You can see in that picture a velocity sensor that's contacting, and that's great. The only issue is when you start talking wastewater ragging and these type of things, you can cause yourself some problems and an extra maintenance visits to clean these. So non-contacting we feel is the best way to go. IP68, because these are going into, especially if we're talking about sewer networks, areas where they could be submerged. So IP68 is a good thing to have with your sensors. Compact. They're going into some small areas. They need to be installed and taken out of these environments. And if you think about a drain cover and the size of a drain and all these type of things, they've got to be pretty compact to withdraw them as well. Rugged as well. They get deployed, and people take no prisoners sometimes when these things are deployed, so they've got to be pretty rugged as well, and very much low power, and I'll concentrate a little bit on that on a few slides coming up. Next slide, please. So yeah, why there are some low power devices out there, and people ask me, well, why can't we use pressure transmitters? Well, we can, and they're good, and they're very good for clean water, but that's a picture I took many years ago, replacing a pressure transmitter in a wastewater lift station, pumping station, and that circle there is the pressure transmitter, probably 5 or 6 times bigger than it used to be, all full of rag and everything like that. So when you're in wastewater applications, non-contacting is the way to go. And as well, if you can reduce the power, then it's a win-win situation. Next slide, please. So how have we developed a low power? And I'll talk about the sensors and how low power they are now. But what we've done is we've reduced the boot time of our sensors. So if you look at a traditional ultrasonic radar sensor, to activate one of these things and power it up, it can take up to about 30 seconds. Then if you're going to turn that off and then you're going to turn it on again, it's very, very power hungry. So what we want to do is we want to turn the power the unit up, turn it on, and then turn it off again in the smallest amount of time to get and also to also get a robust reading as well. And you can see here we developed our dBi range, and we can turn that on now. It can be activated, powered up, and can be turned off again within 4 seconds, which allows us to reduce the overall time of the unit having to read, and reduce the power considerably. And again, I'll come on to that. And we've recently developed a Modbus version, and we can actually wake that up now within a second and turn it back to sleep again and turn it off again. So that really does give us the ability to combine with loggers and to extend battery life in the sewer network system. Next slide, please. So again, looking at this, various loggers here and combination, we're pretty agnostic to any type of telemetry device, so we can connect up to a number of the devices, and people will probably see those and have seen them installed in lots of different sewer CSO applications. So next slide, please. And I won't concentrate and go over this range, but this is the range of our low power sensors, and they all use this very quick boot up time. The IMP on the right hand side was the very first iteration that we did, quickly surpassed by the dBi, because we found that even an IMP, when it went into sewer applications, if it got surcharged, there could possibly be a leakage issue if the cables hadn't been tightened up through the cable glands, these type of things. So dBi, fully potted IP68, and you can see there along the line, probably 1, 2, 3, 4, 5 down, the actual power per measurement. So you'll see there that the dBi, 14 microamp hours per measurement, fantastic. Microflow I is a little bit more power hungry, but still pretty good, 23 microamp hours on a 4-second wake up. You see that now with the Modbus, a digital device. You are talking that 1 second wake up interval, so it gives you 6 microamp hours per measurement. So it allows you to extend, and we were talking about 2-minute wake ups, 1 minute wake up this morning. It will help you with the battery life extension of a telemetry module as well. Next slide, please. So level is great, but when you are talking sewer network monitoring, irrigation monitoring, you want to really talk about flow as well as just level. So we did develop a microflow, what we call the microflow. It's a radar Doppler device. It was developed with Welsh Water many years ago, actually, when they came and sat down in our conference room and asked us to develop something that was compact, that would give them non-contacting, all the stuff that we mentioned before, because they'd looked on the marketplace and there were velocity Doppler radar devices out there, but they were quite large, very difficult to install into a small compact sewer network system. So next slide, please. And you'll see here a couple of pictures there of a microflow I installed. The size of it is pretty compact, size of the palm of your hand, and it's a loop-powered device, and it's actually patented loop-powered 4020 velocity, which we were pretty proud of doing that. It's certified EXIA, so for the sewer type applications it fits very nicely. It's 68 IP68, and again 10 to 28 volts DC, so you can use one of these remote loggers to power the unit without a problem. And the velocity range 0.2 to 6 meters per second. So we move on to applications, and I think these are always powerful to show where these have been working and what data we've got, and some information on that. And again, on their own altogether, what do we do with that data? So next slide, please. This is an application using the IMP, so we're going to talk about all the ones that you saw before, and this is flood alleviation, flood warning, and we've put hundreds of these in Japan. Japan is an interesting island. It's very tall in the middle, and it slopes off into the cities which are around the outside on the coast, and they get very big issues with regard to flooding, and we deployed a lot of IMPs with a logging company in Japan, and they can get now some very good data, early warning data on potential flood occurrences happening, and they can do mitigation with regard to that, opening gates, closing gates, depending on what they want to do, diverting the water flows. So yeah, that's a very interesting application there. Next slide, please. And here you'll see a microflow and a DBI in an irrigation application in Portugal. This is perfect for flow. You'll see the channel and the nice straight lengths. Lovely to get that in a sewer network, but that would be quite difficult. But on this application, to get a pretty good accurate flow measurement, utilizing the cross-sectional area of the trapezoidal channel there, and the laminar flow works very well, and that data is then transmitted into the logger. The logger does the velocity area calculation and then transmitted up to the server. I think if you click once, you'll just have a quick video there of that channel and that velocity moving forward. So next slide, please. This is the major thing I wanted to talk about. We've been deploying the microflow velocity sensor in lots of different parts of the world. In the UK, and the application at the bottom there is in Lima, in Peru. where we have a microflow eye and a DBI connected up to a logger. That's monitored down in that's installed into the sewer, and it's monitoring one of the main trunk sewers under the roads of Lima, and a number of those have been deployed to get information and to look at modelling, and also to look at potential blockages as well. So I think if you just take one more click, you'll actually see a video of that actually. Thank you. So yeah, you'll see there that the sewer running quite fast. The microflow eye and the DBI are mounted on the pole at the bottom with the logging device. That logging device polls those two, and the actual velocity and area or level is then sent up to the cloud, and in the cloud there the velocity area calculation is done to give the flow. But sometimes people will just want the separate velocity and the separate level as well, and I'll move on to the next slide please, and I'll explain the reason for that. So you can just monitor level, and some people use AI now, artificial intelligence, to look at the potential blockages occurring in sewer networks. But there's nothing like having the real-time data as well from a sensor to clarify that. So a velocity sensor and a level sensor will give you that, and sometimes it's better to look at your velocity and your level, because if a velocity is slowing down and a level is increasing, you know potentially you've got a blockage occurring. If a velocity is increasing and a level is increasing, then we know that we've potentially we more often than not got a storm. And again, we can check that with rain gauges and these type of things from a data point of view. Next slide, please. And again, a picture of a microflow eye and a DBI, and that is in Budapest. And the right-hand picture is a rat's eye view of the microflow. That's monitoring that old sewer running through Bratislava. Through Budapest. Next slide, please. And you'll see some data coming back now from these, and this clarifies what I was saying before, where you've got a velocity and you've got level. So we are seeing there a velocity signal that's increasing and a level signal that's increasing in 3 different points. So we're pretty comfortable there that that's just a storm surcharge rather than a potential blockage occurring. Next slide, please. And a bit closer to home, this is one of the UK water companies where they've been doing some modelling with our microflow, different level device, going back to a logging, about 50 of these deployed in this water company, and they've just started to deploy another 200 to get real-time data once they've done the modelling as well. Next slide, please. And again, you can see some data from these devices as well, showing flow in green, so the velocity area calculated, the level in red, the velocity in red, and the blue, the CSO level on there as well. So some good correlation of that data. And you can see here where we did some microflow eye testing against a velocity sensor contacting, and again some really good correlation from that as well. Next slide, please. And again, the last slide I think I have here is some work we've done in the PUB in Singapore using a DBI in very small sewers, and the microflow monitoring the flow and looking at infiltration into that sewer network system. Next slide, please. And that's me finished. So many thanks for listening.
Thanks, Ali. There's some great case studies there. Very interesting to see. I think if we move quickly on, so we'll grab some time for questions at the end. Our next presenter is Alex Keys instead of Stuart Tyres. And Alex is from Augvald. Now, I came across Alex probably, about 6 months ago?
Sounds right.
9 months ago, maybe, and went to see them. And I remember the microwave pipe flow meter of about 3 or 4 years ago that didn't have much success. But this is, I think, to be fair, similar, but not as ambitious as it's doing level. But going to see it, going to see Alex and everyone at Augvald, I came across something very interesting. And from there, I'll let Alex take over.
Thanks, Oliver. I appreciate the introduction. As you say, I'm not Stuart Tyres. I'm his stand-in. I'm the Director of Sales and Marketing here at Augvald. And yeah, I'd like to very much thank Oliver in at least 2 ways. We probably wouldn't be here if it wasn't for him. So let me start off by introducing Augvald, because you wouldn't have heard of us. And this is a kind of coming out for Augvald. It's the first time we presented our products to a wider audience. So Augvald is a startup-sized company. We're funded by a serial entrepreneur, and we exist in a kind of network of his companies. Overall, they employ 5,000 people across a diverse range of industries. The team here at Augvald have worked in other companies, and we spent the last 5 years solving one of the really difficult measurement problems in industry, which is the measurement of flare gas, so ultrasonic measurement of gas flow. Flare is particularly difficult. It's required a dedicated team, and over those past years, we've spent $10 million solving these really difficult challenges. As we sit here, we've solved the majority of those issues in that space. The resultant products are launched to the market and doing really well. So as we came to the end of that project, our owners started looking, what's the next challenge? And rather than keep going in the oil industry, for example, he's looked to move towards the world of environmental sensing, pollution protection. So what I have for you today is far from a finished version. It's probably a step on the journey. We think it's a really good step. We hope it will introduce you to Augvald and of course Augvald to the world of water. So here's what we're planning to offer as that first step. Nivor is a family of accurate level sensors for use in the water industry. So perhaps they seem a bit more evolution than revolution in many ways, but we're a small company, things moving really quickly. So today I'd like to present an overview on what these devices can do. Again, I'll give you some examples of real-world applications, places we've got data. And finally, I'll explain how you can get involved in the launch and rollout while we're here. But the key points from this, plus or minus 2 millimeter accuracy on this microwave technology. We do plan an MCERTS application next year, and again, battery powered. And one of the key differences from other people is that we have this clamp-on variant as well. So these are the size of the two devices. Not quite fit in the middle of in the palm of your hand, unless you're a goalkeeper, but fairly in line with what's on the market. That accuracy we're very confident in now, and it's our aim to start an MCERTS application next year. Power is DC, loop powered or internal battery. Obviously, life depends on exactly what you're trying to do, how often you want measurements, but we think 5 years is totally achievable with the right settings. Now, the clamp-on device at the bottom is a touch larger, but it uses almost exactly the same internal hardware. One challenge we noticed where people had tried to develop these in the past was that they struggled at nearly empty and nearly full pipes. We're very happy now that we've solved that. The reliability at the top and bottom end of measurement is really solid. Now, both devices can produce readings from primary flow devices, your RIAs and so on. The clamp-on device also comes with a flow output, which is inferred. So you input pipe size and angle, as the fill, so it will give you an estimate on flow. Not to an MCERTS degree of accuracy, but it's certainly helpful in some applications. I mentioned that this team have a long history using ultrasound for measurement. So it might have been natural for us to kind of take that experience and shoehorn that in here. But I think the right way to do the engineering is to take a look at what measurement principles and technology are out there and select the appropriate one for the application. And as we did that, we found that microwave has a number of significant advantages over other technologies. And there's a summary of them here, but essentially it's that accuracy, stability, and tolerance of external interference and dirt and things like that have really led us to being wedded to this. I'm not going to spend too much time explaining to this audience, many of whom are much, much more experienced than me, where you can use level sensors. But these are the kind of applications we had in mind as we developed and tested the sensor. So from the start, we've tried to consider not just how we can build a good level sensor, that's really, really important, but also how we can provide a little bit more information rather than just data. And much of what we're doing differently is the way in which the sensor unit itself can do some data interpretation. For example, the NEVO is able to analyze some trends and predict losses in pipe capacity. And then it can provide you an early warning of blockages and even predict maintenance issues before they arise. Clearly, we need to make a sensor where cost aligns with industry expectations, but by doing a little bit more, we hope we can increase efficiencies and reduce costs. So something else we've had in mind, and since the very beginning, is the need for scalability. This morning, we've seen a lot of very impressive companies using AI and similar technology to predict network effects based on a huge number of inputs. That's really impressive stuff. It's absolutely not what we do, but we definitely want to make sure that our sensor is ready to provide data to those really big advanced operators, people with data teams who know better what they're doing than we do. So for these customers, we can provide a drop-in level measurement solution, which can provide that layer of data. At the other end of the market, we have an increasing number of micro operators. And a lot of the field trials we've done have been with those people. Farmers who want ideas of runoff, industrial estates who want to check drainage capacity usage. So in those cases, NEVO's been used as a point solution for these applications, easy to set up, and no need for a DCS or SCADA system in those small applications, but you can still get actionable insights coming right from the meter, which non-specialists can make some use of. Let me show you through some examples of configurations. We put together a few accessories. There's a mounting frame in the center here. When I first saw this, I thought the R&D team had decided to put up some net curtains, but it's actually a really good system. So they are extending poles that lock into an inspection chamber. The frame can be pre-mounted on those poles, so it's ready to go. And you don't need any special tools. Push it out, hand tight, make sure it's level, point it at the water. It's extremely quick to go. We got one of our software engineers to fit one in a car park here. It's like 5 minutes work for a software engineer. So if our software guys can do that, I think it'll be really easy for experienced engineers. On the right is a T-piece insertion, useful for buried pipes. There's a grey-coloured plug there, and then the sensor unit just goes in a quarter turn. And on the left, universal brackets. I think we're all familiar with how these work. The clamp-on version of NEVO needs to be pipe-specific, and that allows the curve on the bottom to match the curve of the pipe. Minimal special tools required for this. There's no acoustic paste, special cements, or anything like that. A few options for fitting, and I'll talk about commissioning in a minute, but the easiest is to take a couple of steel tie wraps, get them around the pipe, and pull it tight. Currently, we're supporting pipes from 100 to 500 mil, and it's plastic pipes only at the moment. We think we could go beyond that if there's a clear market. So I mentioned we've got a few sensors already out there doing things, and a couple of these images feature in the videos of data coming up. So from left to right, there's a balancing lake, there's a culvert, and an inspection chamber, and finally a clamp-on installation, which I think is a rainwater pipe. So I've got some videos with some live data running. And in this first video, we're looking at one of our first headed appointments. This is on an industrial estate that's really local to us. The landowner is looking at adding some new light industrial units and wanted some information on how much capacity he had for rainwater disposal. Now, annoyingly, there weren't any suitable inspection chambers which were easy to get to, but the pipe run did get across a ditch, so we used that as an opportunity to test the clamp-on sensor. So this is near St Neots in East Anglia, pretty dry area, and it's fairly easy to identify days when it rained across the summer. This is estimated flow in terms of litres per hour, and like I said, that's estimated from angle, fill, and pipe size rather than being a proper level-based flow. That big spike that's just come in at the end of July, that's the tail end of Storm Evert, which dumped a pretty impressive amount of rain, and that flow rate corresponds to about 17 litres a second. Pretty high. So all that data is coming from one of our prototypes through the pipe, not open channel. We're really happy with the quality of data we achieved with an early prototype. We're really happy with the stability of the system, how it performed in essentially sat in a farmer's field. So early data which shows that through pipe is absolutely possible. The second application here is a different industrial area owned by the same company, more offices and light industry. And this one had accessible inspection chambers, as it was a wastewater application rather than rainfall. So this was down chamber. It's gone back to the previous one. Excellent. Okay, try and run that. Okay. Sorry, it went back to the previous video. So yeah, the industrial estate owner in this case is looking at adding some. In this particular case, there was no particular reason for deploying, just that we know them and they were keen to have one of the sensors, see what we could find. You can see your diurnal data on there, and you can see weekends. It's an industrial estate, so not much was happening. The accuracy is pretty good on this. We're about 1.5 meters from the water level, and we're getting stable readings, sort of 1 or 2 millimeters. Really, from a basic level sensing perspective, very, very happy with that. We did send people out to make sure that was accurate. Another reason we sent people out to make sure it was accurate is that this waste pipe didn't drain to zero, ever. And we were concerned that might be a misreading. But every time we sent someone out, there was indeed 5 or 6 mil of water in there. So what we did early on a Saturday morning, when no one was in the industrial estate, is we turned off the water to the whole site, and then, lo and behold, that pipe emptied completely. So it was measuring correctly, and we expect that there's a leak somewhere, probably a toilet valve or something like that. Incoming metering to the site didn't provide any granular information, so that had never been picked up before. But we were happy again to be able to sort of solve the problem in a real world environment with an early stage device. So, like everything else these days, Neeva will come with its own app. So that will allow for setup and management of the device. It connects to the meter heads via Bluetooth. For your smaller operators, industrial estates and so on, there will be some data analytics included. We also plan for, if people want it, that those 1 or 2 meters they might need could send push notifications to the app for alarm exceedances and so on. Not something we expect the biggest scale operators to need. Something else we've had in mind since the beginning is cybersecurity. So the app uses encryption wherever possible, and it's been designed to ensure that members of the public, even if they can get physical access to the meter, shouldn't be able to adjust the configuration. Even if they can get hands on it and download the app, they shouldn't be able to make configuration changes. We know how hard it is to secure every single site. So it's that app that you use to commission the meters, and it's another area where we'd like to add a little bit of value. The clamp-on is super easy to do because the pipe size input gives you both reference levels, full and empty. So you get that set up before you get out of your car. With any output options, alarms, all those kind of things can be done. When you get to the pipe, clean off the mud. It doesn't need to be shiny clean, but a thick layer of gravelly mud is best removed. Get the meter flat level and then strap it down to the pipe. Connect power and data, and you're away. Any post-commissioning validation you can do from Bluetooth range, and that should be it. The open channel meter needs very slightly more work. Again, you can pre-commission a lot of it. Essentially, the only other part, apart from fitting it and pointing it in the correct direction, is setting your low and high levels using a bounce rate. The rest of the job is very similar, and hopefully with a pre-commissioned meter, good professionals should be able to install this in minutes. As I said, we managed to get our software engineers to do it. today, every Nevo sensor comes with inbuilt 4 to 20 Profibus. We're currently testing compatibility with common devices on the market, things like technoloy, to make sure that we can drop into applications. And the way that we built the sensor inside is very modular. The comms board is its own sort of entity. So it should be straightforward to offer other wired protocols if you need Modbus, and also things like narrowband IoT, wireless and cellular data. Although I took good note this morning of people saying, yeah, it's lovely, but we're running 15, 20-year-old SCADA systems. So it depends if there's a need for these things. It's something this team have experience with. And I mentioned before, we wanted to provide a bit more information to some operators and not just height measurement. So I've now got a little animation highlighting just one example of that. I certainly not going to bore you taking you through all the things that we've got done that we're working on. So this is my last video. There's a longer version both on our website and on the Congress site. And yeah, I don't have time to talk through all these bullet points. I definitely don't bore you. I mean, the system comes with inbuilt memory and things like this. But let's pick alarms and alerts. So firstly, obviously, alarm thresholds are configurable, not just in either absolute level or pipe capacity, but you can also configure how long the exceedance occurs before the system sends an alarm. Maybe 5 minutes or 8 hours is more significant for your application. Then what we're seeing here is capacity levels being sort of bucketed up. There's 5 brackets here. Again, you could have 1, 2, 3, 4, 5 brackets depending on your application. And then the device is able, from the meter head, to produce these analytics, telling you how long each measurement point spent in that particular bracket. So again, depending on your application, that might be that pipe should mostly be empty, or it should be that it should standard run at 10 or 20% full. You can configure the system to tell you how long it's in each bracket. Sort of long-term data trends we can analyze as well. The system can alert you to behavior outside the normal. Again, all this stuff is optional. If you're looking for an accurate level sensor and nothing more to feed into your SCADA system because you've got a great data team, absolutely fantastic. You can definitely do that. If you want a little bit more, we've got options. So finally, and the reason I'm here, how can you get involved? Nice stories, but what do we want? Well, here we've got a stock of version 1 prototypes, both kinds of sensor, clamp on and open channel. Not everything that I've told you about is fully implemented right now. Neither's not CE-marked, and like I say, we haven't started our own sensor application, but we think as a basic level sensor, it's doing all the right things. So we're at the stage where we need more data from real-world applications and field trials to make sure we haven't made any mistakes, that we haven't done anything stupid, and to make sure the level sensing part is working in as many different places and applications as possible. So we're looking for operators, people who need to measure level and want to try one and give us feedback. We'll come and help you get it working. We're happy to be put up on difficult applications against other devices. We don't need your money. What we need is your information, your input, and feedback. I hope it's a good opportunity to be in early and to shape the future of the device and to some degree the company. But more broadly, we're keen to hear your pain points. Are there things that these sensors should be doing for you that they're not? This team likes difficult challenges, and we'd be really happy to talk to you about how we can solve those. So if this sounds like something you might be interested in, we're here. We've got a virtual booth at the Congress. That email comes straight through to me. There's a website with a phone number, which I'm happy to talk to anyone. So thanks for listening. And if anyone has any questions, I'm here with Stuart, our engineer, for the technical stuff. Thanks so much.
So thank you, Alex. Absolutely very interesting to see. Anyone who also wants to get in touch, they can always get in touch with me as well. So on to our last presenter for the day. And I think most of you know Matt Westgate of Vega. And no more introductions needed. So Matt, if you want to take over.
I believe it is a pre-recorded video that's coming up.
So hopefully that will be coming up any second. So whilst the AV, yeah, okay. There we go.
In the WWEM Virtual Flow Forum. We'd like to thank Oliver for giving us this opportunity to discuss the application of MCERT's compact level sensors for flow and event duration monitoring. My name is Peter Devine. I'm Technical Manager at Vega Controls in the UK, and my colleague Matt Westgate is our Business Development Manager for Water and Wastewater. Okay, we're mindful that there is a great depth of knowledge within the Virtual Flow Forum in the field of open channel flow. However, we would like to start with some basics for those who are not so well acquainted with level flow. The sensors we'll be discussing will fall under the Environment Agency MCERT performance standard. This is part 3, which is performance standards and test procedures for water flow meters. You can see a cover of the Environment Agency document there. We're also mindful that there is a draft, a part 5, for performance standards and test procedures for event duration monitoring. And this draft was released just on the 5th of October this year. If we look at the flow applications under part 3, the main applications are intermittent and continuous effluent discharge monitoring, mostly in open channels, and also instantaneous flow for flow rate for such things as flow to full treatment. Clearly, this is a well-established area of measurement. If we look at the latest draft of the event duration monitoring, the EDMs submitted for certification under this standard can be categorized in the following types. So there is a type A, and this incorporates level sensors that provide continuous level measurement beyond the overflow level. Type B is an EDM which basically has a switched output that indicates that the water has reached the overflow level. And there is also a hybrid of these two. So basically a primary device that indicates an overflow and triggers an on-contact sensor to take continuous level measurement. Essentially, we're talking about devices in the area of type A and the hybrid. So let's take a look at the existing range of MCERT's level-based open channel flow monitoring. Again, we can start with a generic controller with a housing. This comes generally with a display, and this could be a simple flow rate and totalization, or it could be slightly more sophisticated. It'll give things such as status indication. It could be color or monochrome, and maybe there would be a bar graph to show flow rates. Controller carries out the flow calculations, and there will be something like a keyboard to interrogate that, to set the instrument up. In general terms, this will have things such as relays for totalization, and it also comes with a mains power supply. A non-contact sensor, such an ultrasonic transducer, can be connected to that. But the ultrasonics may, in fact, need an additional temperature sensor to improve the accuracy class, and maybe the addition of a sunshade or two. However, there are smart level transmitters, including radars, that can connect to controllers such as this. However, the non-contact radar will not need temperature compensation for the runtime compensation. So the non-contact radar and the controllers themselves will have a comms output. So there could be data logging in various different formats. But if we look at it, most of the current level-based flows certificates on the CSA website of this basic configuration. So the flow linearization is carried out inside the controller. We're talking about compact devices. So let's define what we mean by a compact MCERT level-based flow meter. If you look at this photograph, we can see what looks like a very basic level transducer that needs to be connected to a controller to provide the flow calculations. In fact, this is a smart non-contact radar level transmitter with the capability of providing 32-point flow rate linearization computation internally inside that sensor. Or simple, accurate level measurements, but compact. It does not require a controller. In addition to the linearization for flow, it can provide heart diagnostics, including parameters such as measurement reliability. So these compact sensors can be configured either for level or for flow using a simple but secure Bluetooth connection from a PC or a phone or via tablet. Let's see what this app looks like. These are screenshots taken from the Vega Tools app. We're connected to one of the MCerts certified compact radar level sensors. And we've given it a tag number EDM flow to reflect the flexibility of the compact sensor, as we shall see. Okay, the first thing on the application-based setup is to set up the instrument, the radar, to do a particular task. So by selecting an application, in this case, flow measurement in flumes and weirs, the app will automatically configure the instrument to do the correct function. So the app also gives you graphical representation of the application as you move through the setup. So we can see that we're monitoring a flow in this case. The adjustment of the sensor is based on distance from the sensor reference plane, or the datum, which is the face of the sensor. So we set up our minimum and maximum distances. We can then go into a linearization assistant, or a setup wizard, if you like, where we can step through the setup for a particular flow application. So we select flow measurements, and then it gives us a number of options, including the ISO standards, for flumes, for thin plate weirs, and also for broad crested weirs. So in this case, we can select a thin plate rectangular weir, and we can confirm our min-max adjustment. And then we continue to set up the dimensions for this particular primary flow device. So you can see we have the approach width, the plate width, and the plate height. Next, we can select the engineering units we want, the flow units. So in this case, we've selected cubic meters per second. And then we continue through the wizard, and it gives us a summary. And that essentially is the setup completed. When we come out of the setup, we can see on the display here that we have filling height and we have scaled flow rate displayed with the Vega Tools app. So a nice flexibility and good visualization. If we look at a radar sensor with a local display, it also has bar graph indication. You can see the tag number, the EDM flow 01 tag number, and we can see our engineering units in cubic meters per second. If we don't have a local display, we have the possibility of using the Tools app. And here we can see on a phone that we have the filling height in millimeters and the flow rate in cubic meters per second. The Bluetooth connection is secured with a 6-digit PIN for pairing. It uses a challenge response procedure with a cryptographic hash algorithm and random number generation. On top of that, there's an additional locking PIN code that is used to prevent unauthorized or unintentional changes to the setup. These compact sensors have further flexibility when it comes to installation in hazardous areas. The instruments with housings have ATEX certification, intrinsically safe, and the compact sensors have both intrinsically safe but also EXM encapsulated certification. So basically, it doesn't need a barrier. The flow rate and level can come directly from the sensor, so it can be configured for either a flow application or for an overfill application in a very clear setup method. And that leads us to the possibility of connecting these devices to either a battery-powered data logger, a remote telemetry unit or SCADA system, or as we discussed right at the very beginning, it can be connected to a controller with a totalization function. So a lot of flexibility in terms of how these devices can be applied. So what's new? Matt is going to summarize how these compact sensors can be applied in open channel flow and event duration monitoring. Matt.
Thank you very much, Peter. Thank you, everyone, for joining us today. As Peter said, I'm going to talk about 5 features that these systems offer that we believe currently aren't available in the market. And these give some benefits and add value from all aspects of the system's life. So that's from installation, from even before that, from the engineering, the design, to the installation, to the maintenance and the ongoing operation of the system. So first one I want to talk about is the Class 1 performance in all conditions. Many level and flow applications are subjected to environmental conditions which can change quickly and be quite unpredictable, typically during sort of storm events when accurate and actionable data is at its most valuable. So by having a system installed that is very resilient to these different harsh measuring conditions, it allows you to make decisive actions. It gives much cleaner level and flow data. So it's much better data to be able to analyze for planning and for modeling. And as Peter was talking about before, we're really, really reliable and accurate without the need of protecting it from direct or indirect sunlight. We don't have any issues with things like condensation and build up around the sensor. So much less maintenance and a really, really stable signal. Simpler installations, as I was saying before, and helping people to save time and money. Second point to talk about is it's Class 1 certified over a 5 meter measuring range. So a lot of level and flow instruments need to adapt to an ever increasing variety of measurement situations, and some have accessibility issues. Current non-contact sensors, those systems require the measuring head to be quite close to the liquid surface to allow them to maintain the certified accuracy. And this can create some safety issues. So by having a 5 meter measuring range, this enables you to mount the sensor in an easy to reach location, so much better for safety. That coupled with a very narrow focusing, using 80 gigahertz as our frequency, we get a very focused beam. So we don't, by mounting it further up, we're not susceptible to influence of any internal structures and that sort of thing. And that's really, really important. So overall, we've got a lot more flexibility in where we mount the sensor when we're engineering the solution. It gives us a quicker and an easier installation. So that's a faster and a safer deployment of sensors. Third point I wanted to talk about, and this is touching on and sort of reiterating what Peter was saying, it's a standalone Class 1 transmitter. This really comes into its own in some of the event duration monitoring, sort of UMON3 applications, and the requirement for monitoring the lowest spill point to storm tanks. Quite often the location that you need to measure is in a remote location. There's no power. And so it makes it quite difficult to put power in, or it can be quite tricky when you're looking at power consumption of a battery-powered system. So these are loop-powered transmitters, so we don't have to have a box on the wall to give that MCERT's accurate measurement. So this allows you to put battery-powered systems in that really do optimize that power consumption. Ideal, as we said, for remote telemetry and data logging. You still have that 32-point flow calculation that you can take direct from the sensor's head. And by having it as a standalone sensor, it means that you can minimize the amount of technology and infrastructure that you're having to install. If you don't need the functionality of a box on the wall, you now have the option of putting a sensor in that doesn't actually need it. The fourth point I wanted to touch on as well, again, something that Peter was obviously talking about, is Bluetooth. Bluetooth communication comes with all our radars and controllers as standard. And as what Peter was saying, this provides a really quick, simple, and safe and secure way of connecting to the instruments. When we've looked at some of the draft EDM standards previously, there's been talk of being able to, any Environment Agency officer or MCERTS inspector, being able to look at a sensor's display and see its current status with relation to the switch point or the spill point. That doesn't have to be through a physical display. It could be through an app-based display, like what we've got here showing on the screen. Bluetooth really does give a lot of flexibility in how you can set the sensor up from a safe location, and it's just extremely convenient, making sure you've set the instrument up right the first time round. And the final fifth point that I just wanted to kind of summarize on is that when you do need a controller for data logging, for totalizers, for a local display, or for retransmitting the signal into telemetry, we have got the option of a single channel controller or a double channel controller. So here we've got a couple of different applications. On the left-hand side is your spill point to the storm tanks. So your EDM, your UMON3, there we've selected a radar that actually has a display in the head. Coupled up with a radar on the right-hand side on an open channel flow application, we've mixed and matched here. So we've gone with a fully potted cable version, and those two sensors are feeding back to one controller. So that's allowing you to completely maximize the functionality of the controller, maximize the space in the panel. And you've got multiple totalizers. You've got an 8 gig SD card that comes with that. So if you're monitoring data at 1 minute intervals, that's 185 days worth of data. So that's nearly 6 months worth of data at 1 minute intervals. And so it really does offer you a huge amount of flexibility when we're applying sensors in MCERTS applications as they continue to evolve from not just open channel, but to EDM as well. So that kind of summarizes our session. We hope that you found it informative, and we welcome any questions.
We do have one or two questions that have come through the chat. And just for the AV guys, I'm getting the bounce again. The main question was for Alistair. What's the battery life of these devices, and how often do crews need to replace the batteries?
Very good question. We try to reduce the power as much as we can, down, as I said, to the Modbus, which is 6 microamp hours per measurement. We've done a calculation with a standard logger, say Metasphere, Cello, even a logger that's in our group now called the Ranger. And if we're just talking the measurement, the physical measurement, they've obviously got to consider getting the data up to the cloud and all these type of things, which again is going to suck power. Just taking the physical measurement, you're talking up to 10 years, and that's at 2 minute intervals. Just with that DPIM and 1 second wake ups. But there's obviously other influences, and I would suggest that probably you need to talk to the logging companies as well with regard to that.
So, to be honest, we've got two very experienced companies in the level market, in Pulsar and Vega. What advice would you give to Augvald right now? You've seen what they've got. you both know the water market very, very well, and you've both got excellent devices. What advice would you give?
Stick at it. It's a long old road. I see Matt's laughing there, and it really is. I mean, Vega have just come into the wastewater market in a way, and they've got some really good solutions and these type of things. It takes. I remember starting with Pulsar measurement. 23 years ago, I was the first sales guy, and all I could say is stick at it. It takes a bit of time. If you've got a good product, you'll get there, and you're innovative. You will get there. But the water industry, and I do apologise to anybody that's in the water industry when I say they're a little bit like sheep. When one goes, then a lot of them start to go as well. But as long as you've got a decent product, that's the side of it. So, excuse me for calling you sheep anyway as well. So, I don't know, Matt. You can. I'm sure you can attest to that as well.
Yeah, I completely agree with you, Alistair. In terms of sticking it, there's a lot of good equipment out there from a lot of different companies. I think there's application areas where people can excel in different areas, different ways of applying kit. But there are some people in the water industry that are very keen to look at whether things can be done slightly differently, embracing smart instrumentation, moving forward away from sort of maybe traditional ways of doing things and sort of seeing what is the outcome if we do something slightly different. Is it quicker? Is it more accurate? Is it more efficient? Is it giving more reliable, actionable data? Obviously, people have been talking about a lot of measurement points today. But yeah, I completely agree with Alistair. Stick at it and get out there, exactly as you kind of asked on this platform. And I'm sure if the kit's up to sort of the performance, as you say, it'll gain traction.
Just to give you a little bit of an idea from a gestation period, we developed the Microflow I in conjunction with Welsh Water, and I'm going back now 9 years or so, coming up to double figures soon, and we're only deploying it in numbers now, really, within the UK water market. And it does take time. People have to be sort of secure in the knowledge that this will give them the right data, and it's right for them. But yeah, stick at it.
So we've got a question for you, Matt, from Tom Garwood. Your presentation mentioned the installing in remote locations needed the battery power. How do you manage data transmission in these remote areas where comm signals are poor?
Good question. As we sort of talk a lot of time, we're a specialist in the level measurement side of things and the making of and applying of those sensors. We work in collaboration with specialists in telemetry. So some of the projects that we've been doing that are being scaled up at the moment are working in partnership with companies that specialize in battery-powered telemetry systems. They're working on the latest comms, remote aerials for sort of increasing the signal quality where it is low. Some parts of over on the East Coast, even though it's a bit flat, seem to be struggling with some signals and things like that. So to answer the question, we work in partnership with specialist telemetry companies that have different ways of getting over that.
And to be honest, the whole comms issue is challenging in certain areas of the country. I will note that there is a SWIG workshop coming up in, I think, November, December on comms. Let me double check that for you. But that is coming up, and it's around about that. And I think the whole comms issue, especially around communications protocols, is a challenge at the minute. So that's 20th of October. There's a comms and protocols for sensors being chaired by Alex Gray of Thames Water. So yeah, do go and have a look at that if you're interested in comms. And battery life, I think, has come on a lot over the past few years. I'm seeing battery mags which would struggle to last 2 or 3 years. Now they're lasting over 10. So I must admit, everyone talks about big bang innovation, and we're seeing big bang innovation. I think we've seen a huge amount of innovation in flow monitoring in the past 10 years. Radars were never really an issue. They were never really a thought because they were far too expensive. And there's a lot of really, really amazing work that's been done on radars to bring those down into people's companies' price ranges. And what's next? A water company asked me, what can we do for part-filled pipes? Well, we've had a presentation today for level in part-filled pipes, not quite flow. We've had that talk. We had a product 4 or 5 years ago that promised level-based flow in part-filled pipes, but hasn't quite got there. Maybe, as Alistair says, it's another 4 years till that 9-year mark. Maybe I'm not 100% sure, but yeah, there's some interesting applications, and flow management is only going to get more and more and more important. One of the things we've got is, today was the flow forum, tomorrow is the pollution forum, and it's all about monitoring for pollution tomorrow. The questions we had today, why monitor, how we manage, are mimicked tomorrow. And a lot of that's going to be monitoring for pollution. A lot of the FFT issues is going to tell us how the network's performing. So the flow area of the industry is going to be even more essential in the future. What's everyone's thoughts? What do you think? Are we right in flow management? Are we?
I would tend to agree, Oliver. I think flow management, certainly the certification of flow management and MCerts is a big thing. We were dragged kicking and screaming into the MCerts arena. We embrace it now. If you're going to manage flow, you've got to have accurate data, and it's right that people should be challenged on this as well.
Yeah, I'd just add to that. When we started talking to the water industry about 7-8 years ago with our first water radar that was a lot bigger and more expensive than it is now, a lot of people said to us, does it have MCerts? And we said, well, we're using it for level. And we didn't understand what MCerts meant and where it was actually required. And we went off and obviously did a lot of learning, and sort of a lot of those applications we were talking to people about weren't MCerts applications anyway. What that's kind of done full circle now, where we've got MCerts for this range of products, and people are saying, well, it's that stamp of quality and accuracy that then it's outside verified third party. That then gives it additional credibility in where it can be used in other parts of the business. I know Darren has sort of put a question about the sort of the draft standards, and we keep referring to it. Well, every draft that we've seen that relates to the EDM is about the accuracy class from a non-contact sensor, which this product is more than capable of. Obviously, companies are having to make decisions as to what they put in, down to timescales that they've got, and trying to future-proof themselves. And so that's why we kind of keep talking about it, because as far as we're concerned, and we're aware we're offering something that will tick the boxes.
It's important. I mean, a lot of people don't realise that the investment cycles of the water industry, and Alistair said 9 years. There's a reason for that. It takes time. what you're going to install, you're going to install in bulk. A WWEM2 was 1,000 sites. WWEM3 has got to be around about 3,000 sites. So that's a big investment, and I think we've got to remember that the cost of the actual instrument is a fraction of what it costs to install it as well. So these are big investments that the water companies are making, and so they naturally they want that stamp of quality. Of course they do. Now, is there any more questions from anyone? I've got something. James Luckett saying, have you used satellite comms with your kit?
Not that I'm aware of yet, but our instruments aren't fussy what they get, what they connect to. So we'd be more than happy to. We'd be more than happy to look at that.
We've connected up to loggers, and I think Matt's right with what he says. We're kind of agnostic. We're experts in level and flow and velocity and all these type of things. We leave it up to others to get the data out of the ground up into the cloud. And we've actually connected to a number of devices where it's been very remote in Australia, in Texas, in the States, where they have used satellite, and it's worked very well. But that is, I guess maybe it's a good session to have, Oliver, for logging companies, and to come on here and talk about their comms and how robustly they get the data up.
Yeah, as I said, the next comms session is the SWIG webinar in October, towards the end of the month, and I know that it's going to be brought up in there because ground control, which Matt Westgate is leading in that. I know they work with Immersat and the likes. And realistically, on the comms issue, I think it's going to be a combination. Yes, it's going to be satellite. Yes, it's going to be radio. Yes, it's going to be GSM. Yes, it's going to be probably 5G. We've got a point made here by Andrew Chappell. MCERT 3DM planned to be a requirement from 2025. So that's the WWEM3. I think a lot of current flow, I'm going to correct me if I'm wrong, Andrew, and do put something in the chat, but probably a lot of the certification that are already certified for flow, level-based flow, hopefully will be automatically grandparented over to WWEM3. And I'm sure a lot of the manufacturers will be looking at the product standard, and I know a lot of the water companies will be as well, now that we've seen a version of that. And we can take it from there. And yeah, there isn't a WWEM3 standard at the minute, but hopefully I think most of the level-based flow that's already certified for level-based flow will be automatically grandparented across. Hopefully that will be the way it works, but I don't think any of us know yet.
What we're seeing is a lot of people future-proofing, Oliver, and I guess Matt will say the same thing, and they're asking for an M-certed EDM. And we're supplying to a number of the water companies now a device that we saw the draft, and we developed something as well as Vega did. Pays your money, takes your chance. So
I mean, to be honest, when I see a lot of the devices on there, I don't see why it wouldn't be, to be honest. There's some absolutely great devices out there, and I mean, I started with Anglia in 2012, and I think it's the whole industry's jumped on leaps and bounds, really.
Agreed.
Which is great. Mark Swain, improvements in internal data storage, the Pulsar SD logging have been a big help in some of our more remote and troublesome sites in respect to comms. Yeah, absolutely. Comms has always been an issue, it always will be to a certain extent.
Yeah, it's something that we put onto the Ultra 4 was oodles of logging. And again, I know Matt mentioned it as well. So if you do lose data, you don't lose it completely. You might have to send somebody out in a van to gather it, but it's there.
Yeah.
And you don't have those gaps. And that has helped a number of the water companies gather that data.
I must admit, one of the really nice innovations I saw was dynamic logging as well. So when an event is triggered, probably by the relay, that dynamic logging happens. That it moves from 15-minute data to 1-minute data or whatever. And I think that's one of the really lovely innovations I saw, because it helps the storm events.
Yeah.
More and more with UMON 3 and UMON 4, we're going to have to record those storm events. And yes, it may well help the SAMs of this world who want as much data as they can get. As you say, it could be pick that up from the device afterwards, and with the Bluetooth, with the everything else that's been developed now, it's a wonderful way of doing it. So unless there are any more comments or anyone wants any other discussions, I'll say thank you very much to our speakers for this last session. Thank you very much for our speakers for the day. I think it's been a fascinating session, and I hope you've enjoyed us. If you're interested in wastewater-based epidemiology, the next on this channel will be exactly that. It's going to be a fireside chat with some of the global experts on wastewater-based epidemiology, and literally asking the question of, well, we've had it during the pandemic. Do we need it moving forwards? Open question. I don't know the answer. I'm not an epidemiologist. But if you're interested in that, do stay on. Tomorrow we have the pollution forum, exactly the same format as today. Different set of speakers, of course. And we're also talking about net zero tomorrow afternoon in the 3 o'clock roundtable time slot. So at that, thank you all very much for coming. Thank you to all of our speakers, and enjoy the rest of WWEM. Do visit everyone's stands, virtual stands. I'm sure they'll talk to you for hours about what they have to offer. Thank you very much, everyone.
Thanks, everyone.
Thanks, Oliver.
Thanks.